Today we are having a session of Dr. Minal Bachute, ma'am. Let me introduce Minal Bachute, ma'am. Dr. Minal Bachute, ma'am, is Associate Professor and Liaison Officer at Symbiosis Institute of Technology, Pune, India. She has a master degree in digital electronics and PhD in study and analysis of adaptive filters for speech enhancement applications. She has teaching experience of 20 years, 21 years, and has guided many graduate and postgraduate students with their projects. Her areas of specializations are digital signal processing and adaptive signal processing, AI and ML. She has presented her work at many international workshops and conferences. Her research papers have been published in reported journals and national and international conferences. She was one of the invited speakers at seminar on AI awareness among engineers and students, jointly organized by IET UK and Character Engineer Pacific, means CEP, on Jan 18, 2020 at Langara College, Vancouver, Canada. She had also given a presentation on the role of AI in smart cities to the engineers and technologists at JE Power Engineers, a leading engineering service provider to BC Hydro, Richmond, BC, Canada on Jan 17, 2022. She has also conducted a webinar on AI for IET, Trinidad and Tobago Network in Jan 2021. She is actively associated with IETE, IE, IET, and other professional institutions. She has published her research work in reputed journals. So, welcome, ma'am.
Thank you so much, Deepak. So kind of you. And good afternoon, one and all. Am I audible? Clearly audible?
Yes, ma'am, you are.
Yes. Let me share my screen. Hope the screen is shared.
No, ma'am, it is not visible.
Okay, okay. Let me share it again. Hope the screen is visible.
Yes, ma'am, it is clear.
Yeah, perfect. Thank you so much, Deepak, and good afternoon, one and all. Here, myself, Dr. Mrinal Bachute. Of course, I'm very much interested to work into image processing, speech processing, applying artificial intelligence, machine learning, and basically at the algorithm side. I have done extensive study. Of course, the study continues along with my research students, PhD scholars, and then BTech, MTech students. As we say, learning is a continuous process, isn't it? Learning never stops. So today also is a very excellent, wonderful learning session, wherein I would like to discuss certain basic concepts related to linear regression, KNN, and K-mean. Apart from that, I would be very happy to collaborate uh, with you, wherein you can think, after we discuss this, where and in which domain you can apply these algorithms. So at the beginning I make it very clear that whenever we are discussing this linear regression, KNN and K-mean algorithms, you also have it in your mind, because see, each one of you might be working in a different domain. Maybe different applications could be biomedical applications, could be automotive applications, or n number of domains, right? So let us begin with the today's discussion. And today I'll be focusing on these three aspects. And towards the end, I will also talk about not only at algorithm end, how to improve the performance, but at the data end, at the parameter selection end. So we will be having certain insights into how to make our system better, because see, we all know human system, right, is the most intelligent system, isn't it? We as a child, we learn from our childhood, like whenever a small baby is born, he or she learns through experiences, right? The way you are exposed to the environment. Suppose a baby sees a fire, or maybe a small lamp, and gets attracted towards that lamp and try to touch the lamp. what will happen for the entire life? The baby will learn that no, you don't have to touch the lamp, otherwise your finger gets burnt. Of course, we will not allow the baby to touch the lamp because the mothers and the caretakers are taking good care. But just one example, an analogy which I would like to share with all my participants, that the human brain learns कि never in lifetime the baby will go towards the lamp or touch the lamp, right? So that is the human algorithm, how it learns. So I basically work more on the algorithm side. Of course, there is now a new trend which is coming up, wherein we need not only have access to the algorithm, developing the algorithm, hybridizing the algorithm, combining the algorithm, or coming up with new algorithms. This is not only one way. Apart from that, working on the data set, fusion of the algorithm with the data set, and not only with the dataset but the parameters which we select. So all these synchronization of all these three can make our systems better. So moving ahead, today, as I said, we'll be talking about linear regression, a simple regression model I'm talking about over here. You can see that you might have come across like a particular data set, and you wonder, oh, which model will I use? It totally depends upon what data set you have, how much extensive the data set is, whether you want to use the supervised learning method and unsupervised learning method, right? And of course, towards the end, we will be also talking about when to use linear regression, when to use KNN, and when to use k-mean. And then the third very unique methodology which I'm talking about is fusion of all this, like not only using these traditional algorithms, fusion of these algorithms or hybridization of this algorithm and coming up with some new method. This is, of course, the researchers are doing this kind of processing. But apart from that, there is something which comes a very different approach, wherein we are also going to have certain interventions from the data set which is available for our application, and then processing it in line with all these three dimensions. So very interesting concepts we'll be talking about, right? So to begin with, whenever we talk about a simple regression model, of course, we know the expected response, which is indicated by E of y by x. Then you might all know that there's a linear component which is present. You can see the cursor moving. This is the linear component which is present. Then we have a random error, that is error in the model, wherein we need to estimate this error. And my dear participants, why this error is important? Because we need to know what is the actual value and what is our model estimating, and the difference between that is nothing but our error. And what do we want? Generalized principle is that we want this error to be as much minimum as possible. Of course, we know that this is a random value and this is the linear component. And now when we deep dive into this linear component, you can see that we have beta 0 estimated value plus beta 1, of course, again estimated value. And here we have independent variable x. Now here, why are we using regression model? Most of you might know that simple regression model considers a single regressor or a predictor x and a predicted or a response value y. So at a very aerial view, I must say that what are we trying to do is there are certain variables. Say there are two types of variables. One is independent variable and the dependent variable. We are trying to build in the relationship between this. So what I mean to say over here is, whenever we are talking about this independent variable, this could be, say, a company whose estimated, so best example which I could give is turnover, predicted turnover. Okay, so now this is an independent variable, predicted turnover. Now the turnover, which is an independent variable, that is driven by certain dependent variables, right? The dependent variables could be investment towards innovation, investment towards R&D, investment in what we can say, investment in the manpower, then the investment in the maybe XYZ parameters which drive the turnover of a company, right? So here we are trying to build a model and trying to build a relationship in a way that we will see that out of these X1, X2, X3, X4, X5, all these parameters, which parameters directly affect the turnover of the company. And not only, see, it is quite possible, maybe one parameter, two parameters, three, or combination or fusion of these parameters would affect the turnover of the company. Okay, so this is what, and then on the basis of this, we develop the model and we try to predict, say, forecast that, okay, so in 2022 this was the turnover and these were the parameters, and on the basis of the plan, investment plan, what we can do is we can predict the outcome in the year, say, 2023. Right. So this is a very interesting example which immediately came to my mind. So I thought I will share with you. Right. So whenever we are talking about the regression equation, this is only an approximation to the true functional relationship between the variables, as I was telling you. Regression model is empirical model. There are two objectives, as I said. We have an estimate, the unknown parameters, which I was talking about, right? B cap, B0 cap, and B1 cap, which is the estimated value. Fitting the model to the data is very, very crucial, very important. And sometimes what this method do is, of course, it starts with this method only, method of least square. So this is how you go ahead with B0 cap and B1 cap, estimating the value. And what we do is an iterative procedure is followed to choose an approximate regression model to describe the data which we have at our hand, right? So, as I said, least square estimation. So, point may come to your mind how to calculate it and what are the mathematics behind it and how does the values B0, B1 obtain and how do we find B0, B1? Basically, it is it minimizes the sum of the squared residuals. So, we can see in this particular formula, like suppose you have the data points here, you may try to fit a model which would be in line with this particular method. Maybe a line can be drawn like this, or you may choose to draw the line like this, or you may choose to have it in this particular way. So maybe however you choose, but in this particular method, when we are trying to estimate the linear square estimation, what we do is we minimize the sum of the squared residual. And this is how, of course, I will not go much into detail because this is very basic thing, right? Moving ahead, how and what defines the model adequacy? Fitting a regression model requires at times several assumptions. And what are those assumptions? First of all, errors, which have constant variance, which is called as homoscedastic type of errors. And there are certain errors which are uncorrelated random variables. Now, see, there's a lot of statistics which you all might have studied in the, of course, all of you belong to engineering domain. So I must not go into so much of basics when we talk about random variables. But let me tell you one or two insights wherein, see, whenever we are talking about data, what is actually dealt with in general, practically, either you're working on the image, or you're working on the speech, or maybe you're working on the video, or maybe some three-dimensional data, two-dimensional data. And ultimately, when you're taking that particular data sets, it's ultimately at a basic core level, it is nothing but numbers, right? And this variables, random variables, you are going to use the statistical methods to process this, right? So here, fitting a regression model requires certain assumptions. So those kind of assumptions, which is homoscedastic, non-autocorrelation, or it could be white noise. These are the general assumptions which we take. Then probability plot is also very important, wherein we are checking the normality. H0, the distribution is normal. H1, the distribution is not normal. This could be the two situations, right? And then there are certain tests. Maybe most of you might have heard about these tests, which is most popular test called as KS test and AD test. Shapiro-Wilk test is also used in many situations. So these are the normality checks which are being done for this kind of linear regression models. Right now, let me discuss with you one example wherein suppose you have certain data points. Say this is the actual data point, and then on the basis of the statistical analysis, you predict like what we did in our DSIR research project. What we are doing is we are considering the load, how much it is utilized, and we are trying to predict on the basis of the data which we have: hourly data, half hourly data, monthly data, yearly data. We are trying to predict the and forecast, of course, what would be the requirement in the next week, next month, next year, on the basis of this. And let me tell you, all of my participant friends, the success of it totally depends upon how much accurate and better and relevant the data is. Right now, suppose we are using the statistical methods and we predict this particular value. Right now, here you can see the cursor moving. Now, on the basis of all the analysis, maybe I am talking about in context with one predicted value. Right, I am predicting this particular value. Right, I forecast or I may predict that, okay, so this is the value. And you may actually validate it in actual environment with electricity board and just check, right, what is the actual value. So say, suppose my algorithm or my model is predicting, my linear regression model is predicting this value, and at actual, this is the value. So you can see there is a difference between the actual value and the predicted value. Of course, there is a chance for fine tuning the prediction and bringing that prediction as much closer as possible. So this is the predicted value, this is the actual value, and bringing this predicted value as close as the actual value with the help of the advanced techniques which are present in the linear regression. Wherein what we do is we calculate SST, we calculate SSE. This is the difference between the actual value and the predicted value, and then you can see that the average value, y cap or y dash, and this is at x-axis we have x iterations, y-axis we have y iterations. And then what we try to do is we try to reduce this distance between the predicted value and the actual value, and we try to bring this predicted value as much close as this actual value. And in the process of fine tuning and bringing this value towards the actual value, this SSE value becomes as much minimum as possible, because that is what is the ideally we require, that this value should be as much minimum as possible in order to have a better and better predicted value which is approaching towards the actual value. And this is not going to happen suddenly. This is going to happen with, say, first iteration may give you some value, and again you have to validate it. After validation, you may understand that, oh, it's far away from the actual value, so the error will tell us that's far away. Then again you need to go for the next iteration. Then again checks at different levels. What is the data set? What is the algorithm? How fine tuning I can do at the algorithm? Which parameters I have chosen? Have I chosen correct independent parameters? Am I working on a correct dependent parameter when I'm talking about linear regression, right? So far so good. So this is how I wanted to, discuss at a very basic level what we do whenever we are trying to predict by using the linear regression. Now, a point may come to our mind when to use this linear regression. Linear regression is a machine learning algorithm which is based on supervised learning. So it performs a regression task, right? We know this, right? Now, linear regression is mostly used for finding out the relationship between the variables and forecasting. So now here, I would like to pause for a minute so that all my participants will try and maybe you are working in different research domains and try to bring up certain examples in your mind. I gave one example: load forecasting, load prediction, then power consumption prediction. uh, in this way, you may pause, think of certain applications in your domain wherein you can fit in or wherein you can use linear regression. So maybe I request the coordinators, if possible, unmute so that participants can discuss what application come to their mind, because I want this particular session to be very interactive so that the takeaway is more. Is it fine? Can we unmute the participants?
Yeah, sure, ma'am.
Yeah, thank you so much.
Madam,
Yeah.
Yeah, Ami sir, would you ask? You are asking
yes,
something?
yes.
Yes, yes.
This is for weather prediction, weather forecasting. Yeah, we can use for the market analysis.
Yes, market
For
analysis.
yes, for
Could we share
price
market?
prediction. Yeah,
Perfect, perfect.
maybe share market or for electricity price prediction.
Correct, absolutely. I'm very
Yes,
happy. So whatever I have discussed, it is very nicely taken. That's the reason I thought that this should be very interactive. Yeah. So it is. If I'm not mistaken, this is from Amit Kukkar sir.
yes, yes, ma'am.
Yeah. Thank you so much. Also, I would like some other examples, and then we'll proceed ahead. Market prediction is one thing. Then price predictions is also a very good example. Anyone else? Deepak, would you like to throw more light on how we use linear regression in our research project? A quick insight
Yeah,
into
yes,
in a
ma'am.
minute
Yes,
or
ma'am.
half
So we
minute.
are using, we initially use this linear regression for load forecasting for electricity. So basically, you will be glad to know that ma'am is helping us in this Bharat Sarkar project, which is DSIR funded project, electricity load forecasting. So initially we
Yeah.
used, so this is initial method that we used to segregate what
Yeah,
data.
we tried and we used a linear regression, basically regression model, and that was a very starting point. That we just try to understand how our data is behaving, whether it can be fitted in this linear regression model, and try to find out which parameters are important and how they are related. And we tried to forecast, and yes, we are getting better
Yes,
results.
ma'am, and yeah, we took independent and dependent parameters as well for that
Yes,
forecasting
yes.
model. Yes, ma'am.
Yes.
So
Can
we
you
use
tell which are the dependent variables and independent variables so that we
a
can move ahead
dependent
once that
variable.
is
Yes,
discussed?
yes, ma'am. Load is
Yes,
the only dependent variable which helps you
correct.
to
That is
forecast.
the main agenda of
Yes,
the entire research.
yes, ma'am. Yes.
So that was the main thing. As I explained in the initial stage, that suppose there's one industry and predicting the turnover. And I said that there are so many parameters which are affecting the turnover. And if at all you find out which parameter is most important, being the owner of the company, we can decide the investment in 2023, which are the crucial parameters affecting the turnover. And accordingly, we can plan the strategy for 2023. Thank you so much, Deepak. Thank you so much, Amit sir. Moving ahead, let me share my screen. Yeah, my screen is shared, and let me move ahead. So we were talking about, I was just trying to make this interactive because, the attention span, it is so much researched about. It's like 20 minutes, 15 minutes, 10 minutes. Of course it varies. So overall there's a research that the attention span varies between 15 minutes to 20, 25 minutes. Of course, with the youngsters, again, it is very less. So I thought let us have a very interactive session. Moving ahead, my dear participants, let us talk about K nearest neighborhood. Now, what is KNN? Right. Why do we use KNN? In which situations we use KNN? Initially, I did say that whenever we are talking about data set or real world data, um, what could be the data? Irrelevant of application in the universe, what could be the data? See, I'm speaking, that is one data. Speech is the data. Maybe I'm taking a camera, I'm capturing the image, satellite image, drone image, in case of some um, what we say agriculture applications. I may use drone and capture some images, right? Then in case of natural language processing, what could be the data? The text, the speech, right? Of course, whenever you talk about any application, what comes to your mind? How do we convey information to each other? We convey the information either in the form of speech, image, right? And then combination of it, video. Video is nothing but the frames, right? They are repeated, the images, the repetition. Ultimately, what I mean to say is the data could be at a very simple stage. The data could be speech, image, or could be a text, right? And of course, whenever you're processing the text, again, you're taking the images of the text and then trying to find out the patterns in it. Now, when the data is two-dimensional data, of course, we can work on three-dimensional data also when we're using KNN, that is called as K nearest neighborhood. The name itself tells us that it is nearest neighborhood, means here you are trying to focus on the nearest neighbors, right? Suppose there's one particular point over here, you can see the cursor moving. So this is the x-axis, this is the y-axis, and I say, of course, I can work on three-dimensional data also, but for simplicity, I am choosing two-dimension data, right? So here I indicate a data. See, this is the data point, which is indicated by cross, red color cross, right? These are the data points. And another set of data, which is indicated with purple. Okay, so we can see these purple crosses, right? So these are the two different data sets. Of course, all the data set is say two-dimensional data. Now, if I want to say categorize or say I have one more data point, say these are the already existing data points which are indicated by a red color, and the data points are indicated by purple color. Now, my dear participants, what is my intention to tell you here, or indicated with two different colors, is to differentiate between two different clusters, right? And there is one query. Suppose there is one point which is indicated by a gray color. This is the query, right? And we try to find out the distance between this query. So this, what we do is, so K nearest neighborhood method we are applying, and query point. There are two categories. What will I say? Say this is one category, I'll call this as category 1, and this is another category, I will call this as category 2. See, at a very simple basic level, what we will try to do, our data point, right? We will see where our data point is. See, everyone, please focus. This is our query. And what we try to do, we try to find out the nearest neighbor. This is my point, and I will try to find out which are my nearest neighbors. Now, of course, this is a very limited and very simple data. So immediately, by your naked eyes, you can see that this is the query, and maybe this point is the nearest, because the distance when you calculate between these 2 points, this would be the nearest. Then this is the nearest one. This is the nearest point. Then again, comparing, maybe this is the nearest one. This is the nearest one. And then this is the nearest one. So these three and these three could be the nearest one. But when you compare these three, maybe these two are the nearest, and then this is the far away, because the distance is more. So let me give you the visual effect. Now, considering the K nearest neighborhood, say for example, kitne neighbors find out karne, how many neighbors we need to find out. Say I consider in my example that K is equals to 5. Means what? We are supposed to find nearest 5 points, calculate the distance and find out the neighbors. Neighbors, kiske neighbors find out karne hame? This is the query. So this is the point and I'm interested to find out my neighbors. Who are my neighbors? So for example, as I have considered k equal to 5, of course you can change this as per the dependent upon the data and the application at hand. But here what I choose is k is equals to 5. Right now, this is my query, which is indicated here, and this is the nearest point 1, 2, and 3. Right? So 3 points here and another 4th point and the 5th point. Now I have to find how many points? I have to find my neighbors. How many neighbors? 5 neighbors. Why? Because my k I have set to 5. Interesting? Sorry, I just missed that. Can you see?
Yes, ma'am.
I'm so sorry for that. Yeah. So what I'm going to try to do is I'm going to find the neighbors. So we calculate the 5 neighbors. Right? Now, once we find the neighbors, fine, we have found out 5 neighbors. Then what will we do? Once we are finding the neighbors, what we try to do is how many of the neighbors belong to which category. Here we have 2 categories at hand, category 1 and category 2. So in my example, what is here is these 3 neighbors belong to category 1 and these 2 neighbors belong to category 2. Right? So far so good. Now better. I am understanding this much better because more number of data points from category 1 are the nearest neighbor to my query, X point, this particular point, and 2 neighbors, rather less neighbors from the category 2. So what does this mean? Now see, if maximum number of points belong to say category 1, then the query belongs to which category? It will belong to the category 1. This is how this particular model works, right? And so far so good. Once we understand that, we know that this particular point, data point belongs to category 1, our model is ready, right? Ready to go. In this particular way, if another query arises, that is data point comes, you are going to calculate the neighborhood. And this particular thing we are repeating for each and every model, right? For each and every, each and every data point which is present, right? Go on repeating iteratively and then categorize, right? So in this particular way, we are able to work on this particular 2-dimension data. Once the model is ready, we move on and then we again categorize whether it belongs to category 1 or category 2. And in certain points, you may have more categories also. Now, when I say the neighbors, a point may come to your mind, how to calculate the neighbors. We all know in our engineering, in our research work, or maybe in mathematics also, most of us have worked on this, right? Calculation of distance. So majorly, of course, there are so many other methods, but at a core level, basic level, you calculate it by using Euclidean distance, then Manhattan distance. How in case of KNN? Basically, we use these 2 different distance calculations, Euclidean distance, and we are very much aware how do we calculate the Euclidean distance. Say distance d is calculated. Say, for example, you have x-axis over here towards and the y-axis over here. This is the data point. This is another data point. And how to find out the distance between these 2. Can you see the cursor moving here? So this is the distance between these 2. When I say this is x1, y1, this is x2, y2, how will I calculate the Euclidean distance? It is equals to under root of x2 minus x1 square plus y2 minus y1 square, right? And this is how I calculate the Euclidean distance. Then Manhattan distance. Now here, these are the points, but not, we don't do certain subtraction directly, but what we do is we try to calculate this length and this particular length and 90 degrees. And then with the help of this, we calculate the Manhattan distance. Now, once we are ready with our model, we again understand what is the data, whether our KNN method is going to help us. Say, for example, you require most accurate model. Say in your context, accuracy is very important. So KNN can help you to give a better prediction, accurate prediction for your application. But there is one glitch, one problem. The quality of the prediction depends upon the distance measure. So therefore, KNN algorithm is suitable for applications for with sufficient domain knowledge, because see, we need to have the intervention in that particular data set. So the domain expertise, domain knowledge is very much required for the success of this particular type of method. So this knowledge supports the selection of an approximate measure, and most of the time this algorithm is also called as lazy learning, because it is very much, where the computation of generation and prediction is like, differs until the classification. You take one data point, calculate the distance, and again you go on the classification. So at the computational side, if you talk about, the cost of computation is tremendously high, because complexity is high, because there are so many permutations and combinations which one has to do, right? So but still, even though it is computationally very, very high, but still it is a better choice for certain applications where accuracy of prediction is very, very important. And that's the reason KNN is still used, not purely, but maybe with fusion or combination with the algorithms. Of course, KNN is purely used also for prediction. Then moving ahead, so here, you also should think at this particular point when you can use KNN in the domain of application which you are working at hand, right? Is it requiring the accuracy to be very high? Do you have that domain expertise whenever you are having interventions with the data set? Do you really understand the data properly? Maybe the image data, speech data, whichever data you have at hand, or the load data which is available from the electricity board. Then you can decide if accuracy is very, very much important. You can use KNN method, right? So my dear participants, there is third method which I would like to discuss with you is k-means clustering. Most of you know clustering, right? And what is k-means clustering? And say, for example, being researchers or being with students, a particular example comes to my mind. Say, for example, attendance of the students. Say the data is very scattered in a way that in a class, students are attending certain lectures and not attending certain lectures. And say, for example, internal component results are declared and semester results are not declared. Am I able to predict, is there any relationship between the success of the student in end semester results, based on the attendance and the other parameters, internal component and other parameters? Am I able to find out the clusters? Maybe, see, this is not a very easy problem, because there are many dependent variables, right, on which the success of the result prediction depends. Say, for example, I use k-mean clustering for, say, given data of student, wherein what I do is averaging, right? 3 points survey. Say, suppose I have 10 to 20 questions, and along with that, attendance, this questionnaire, internal marks, I try to plot it. Of course, it's a very scattered plot, which would look like this. Very interesting problem, though very complex. How many clusters we can make from this data? How many clusters? Any answers? Can we unmute the participants? Because the data is totally scattered, isn't it? Earlier data was very, very properly distributed into two clusters, right? And initial, when we were talking about linear regression, then it was linearly distributed, and we were able to draw a line properly in order to classify or cluster the data, right? So here, there are so many clusters that can happen, right? So the basic problem is the plot is very scattered. Then how am I going to cluster the data? Hope everyone is understanding what I'm trying to say here. Moving ahead, what I will do is say I have to do certain assumptions and I have to begin somewhere, isn't it? So we usually start with, say, let us assume, isn't it? So over here, what I will do is I will use two random points. Say this is one random point which is indicated by red dot. This is another
Hello.
dot. Hello.
Yes, ma'am. Suppose this k value is 2. So I supposed to just make the two cluster and find out the mean of the
Perfect.
cluster.
Perfect.
And then after that, I need to find the distance of each point with these two. Suppose this point,
Centroids. Centroids.
centroid,
Yes.
centroid.
Perfect. Yes.
And then again need to find the mean in distance, and then make
Yes.
a cluster again and again. Is a repetitive.
Yes.
The problem is every time we need to make the centroid. That
Correct.
is the thing.
Perfect. Perfect. That is what I was intending to say. So that is the major problem over here. So as I said, very correctly said just now, that it is an iterative process. What we do is we have certain two random points as a centroids. Then what we do is we calculate the Euclidean distance for of each data from the centroid. Say for example, this is the point, this is the point, these are the 2 points which we are assuming. Then the point near to the centroid are formed as one cluster. So for example, say this is the point, the immediate point which is very near to this is this particular point. We calculate the distance, and then what we try to do is all the points whichever are near to this particular centroid, we try to group it into one cluster. Very interesting. See, then what we try to do is we move our attention towards the next centroid. This is the centroid. Again, we calculate the distance between the data point and the centroid, and try to group all the data points which are near to that of that centroid, this centroid. And then we try to build the cluster. Okay, but again, if I try to have different centroids, these two centroids, but now if I feel that I should have two centroids at this particular points and then have the clustering. Again, what I have to do is see the centroids, calculate the distance between the centroids, and cluster or group it as one cluster. Again, once you're grouping it into one cluster, see, it's a very interesting thing. What we have to do is group it into one cluster, repeat the process, again calculate the distance. And sometimes you may realize that, oh, this was the centroid, right, which we assumed, but that is not the case. Now my new centroid has moved to a different location, right? So let me show you that also, because we are considering this example, as I said, attendance and midterm marks or end term marks, end semester mark prediction. It's a very complex problem. So these are the centroids. Now here I am taking, maybe I may take 2 points, 3 points, C1, C2, C3, and then calculate the nearest values and then cluster it into maybe one, 2 or 3 clusters like this. It's a very interesting problem because this is not sufficient. Once you are calculating it, oh, this is one cluster. We started with some assumption. Always that assumption might be true, might not be true, right? So again, you have to reiterate, again calculate the Euclidean distance, repeat that particular process with, say, another example, C1, C1, C2, C3. Again calculate it, right? Now I will form 3 clusters. Perfect. Now what I have done is, initially I thought it will be classified into 2 clusters. Then I realized no, 2 clusters are not sufficient. Here there are 3 clusters. And what we do is we find out that, yeah, there are 3 clusters which are existing with initially assumption that C1, C2, and C3 are the centroids. But after few iterations, I realize that my assumption of the centroid is wrong. Is wrong in the sense I need to fine tune that. C1, C2, C3, I need to fine tune and calculate the new values of the data point. Then I realize after getting all the data points, averaging it and finding out that, oh, this was my assumption, but reality is something different. My centroid is not C1, but it is C1 cross, which is indicated over here. Oh, then this is the case. Then again start the next, in the next iteration, again consider that C1 cross as the centroid, again repeat the same process, right? And then fine tune the cluster and see which data set belongs to this cluster on the basis of nearest point. If it is nearest to C1, group it into C1. If it is nearest to C2, obviously it will be grouped into the C2 cluster. Very interesting. Now, my dear participants, a point may come to your mind, कब तक करना है ऐसा? Till what point I have to do like this? Very interesting. Look at the data point which you have. Look at the application. What is your requirement? What is the threshold you are very happy with? Right? या तो one thing, do it till the new centroid and the old centroid is same. मतलब इसके आगे कुछ नहीं हो सकता. No correction is possible. That is one point to stop. Next point is, this is my threshold. I have done enough iterations, 1,000, 10,000, 20,000. Enough iterations are done. And with this existing data set, with this application, I'm happy with this much threshold, L1 or T1 threshold. Usually we use T1 term for threshold. So T1 threshold, I'm happy with it. Then stop. Or the third point, I will say that in my context, in my data, my application context, I do not want to use these 2 methods. What I will do is, I will set some target. Say I want to do this for 80 iterations. I will do 80 iterations and I'm happy with whatever clustering has been done, looking into the data set. So this is how we go calculate the average and find the new centroid and go on repeating it. Then, as I said, this point may come to your mind, kab tak karna hai ye iterations. So I gave you that when you're calculating or computing the square error function using this particular formula, you go on repeating, calculating the new centroid with new clusters and look and have that insight into the cluster and understand. As I said, ये तो सबके मन में आएगा, कब तक करना है ये, when to stop the process. Again, when you are calculating the new centroid, again you calculate the Euclidean distance, repeat it, and repeat it till the new centroid and the old centroid at the same point, stop. Because इसके आगे कुछ नहीं हो सकता improvement. Because there is no way to move ahead, because you're already at the perfect, proper central place, right? Other thing, centroid is not moving, it's not moving, then stop. And this may take number of iterations, or under certain threshold, T1, T2, T3, whatever threshold you have decided for your application, because you being an expert, when you're dealing with some speech related application or related to image related application, you know that with this particular threshold, you're okay with, because you're getting the results perfect, right? Then you can stop, or stop after a specific number of iteration depending upon the application, as I said, 80 or 40. Okay, so this is how you go deep into analyzing and applying these methods into your application. And now I pause for a minute. I give you an activity. My dear participants, I request
Hello.
you. Yes?
Ma'am, sorry to interrupt you, ma'am. Can you please repeat one more time the point, how our assumption that would be wrong that we took initially? Suppose initially I took the
Yes.
two data point and then find the centroid. So how would be that wrong that we took the initially the data point?
Yes, I will repeat it. Let me go back and repeat. Yeah. So what we are trying to do is we are trying to calculate the Euclidean distance, right? And we initially start with certain assumption that C1, C2, C3 is our centroid. And then what we try to do is C1, who is the nearest neighbor of C1? Then we try to find out C2, of course, the C2 and the nearest neighbors of the C2, and then C3, and then we try to group these neighbors and we call it as a cluster. Say, for example, this is C1, C2, C3. We calculate the values and we group all these samples. You can see the cluster cursor moving. All these sample points which are nearest to C1 as one cluster. Then there are three clusters over here. Cluster 1, cluster 2 and cluster 3. These are the data samples, data points which are nearest to this centroid C2. What I'll do is I'll group it into one cluster, C2 cluster, with, of course, two cluster number 2 with centroid C2, right? Then C3. This is the C3. But suddenly, okay, you started with some assumption. Suddenly, okay, you're in the process of finding out the cluster, but that might not be a better estimate. You're still in the process of learning. You know, na, algorithm, there are three processes, like initial is training stage. Initially you train the data, training phase, testing phase, right? And then again, you try to fine tune it, periodic fine tuning and periodic learning, right? Training phase and the testing phase, right? Now here, what in this process you find out that C1 is the centroid, which we started with initially assuming. But after the cluster is formed, you again calculate. Again, what you do is you take the data points cluster and again you average, calculate average and find the new centroid. जो भी points ये cluster में है अपने ये पहले वाले cluster में, you again try to average out and try to find out the centroid. Then you realize that we started, हमने start तो किया था C1 से, but now in this context of data, you realize after the few iterations that ये मेरा centroid नहीं है, C1 is not my centroid. Then what is my new centroid? How do you calculate? Averaging, जो भी cluster में data samples है, data points है, you have to calculate the average and find the new centroid. Then you plot that new centroid. C1 नहीं है वो, अभी C1 cross है, तो ये है C1. Just I'm trying to show कि there is a deviation between that. So what we do is we find out this centroid and then again try to calculate the distance between the samples which are included in the cluster and again compare whether this sample belongs to this cluster or whether this should belong to this particular cluster. So again, rethink on each and every data point in context with the new centroid. Very interesting it is. Of course, it is complex too, but it is always like, complex things are more fascinating and more interesting. And of course, they help us to solve the problems in practical situations also. So here, I'm calculating the new centroid. Once I calculate the new centroid, of course, computing the squared error function is also very important, because you remember estimated value and actual value and predicted value, there is a difference between these two, and that is error. You need to calculate or compute the squared error function and then again rethink on it. कितने clusters है, कितने data points है, कितना error है, and on the basis of this, every iteration you need to find out new centroids with new clusters, fine tune, and go ahead. Again, you realize that this is the new centroid. This is the new centroid. Okay, and move ahead. Hope it is clear.
Yes, ma'am. Means
Yeah.
every time, yes, ma'am. Every time is centroid that will be changed, no, ma'am. Every time,
Yes.
every
Every
iteration.
iteration, every
Yes,
iteration,
ma'am.
the centroid
Correct.
will change.
Correct,
Now,
correct.
I pause for 2 minutes. I give my research scholars, my participant friends, 2 minutes to think on क्या है ये algorithm, कैसे काम करता है ये algorithm, and the application, और मेरा जो रिसर्च डोमेन है उसमें ये algorithm मैं यूज कर सकती हूँ, कर सकता हूँ या नहीं. Just 2 minutes and how this algorithm works. This is going to help us. I just pause for a minute. Let me, and then I would like some interaction. I will stop sharing. Hope you all are uh, able to relate to what I'm saying. So, good afternoon. Welcome back to the session. I hope I have given you enough amount of time to rethink on how this particular algorithm works, right? And also a thought on um, whichever research domain you are working on, how you can apply this. What is the problem at hand? What is the data set which is available? What domain expertise I have, and which is the application at hand, and what is the objective, right? So moving ahead, let me share my screen. Yes, perfect. I hope I'm audible and the screen is visible. Welcome back, and let's go ahead.
Yes, ma'am.
Yes, perfect. So a very interesting algorithm we have seen. Of course, right from beginning, I had a special, interest towards working on the existing algorithm, developing new algorithm, fusion of these algorithms, because whenever you're working for your research, maybe in your PhD application, or just 1 minute, huh? Just 1 minute. Yeah. Yeah. So whenever you're working, it's always that what is novelty, what is new in your method. So it is always trying to use the existing algorithm, perform the operation, see how the results are coming. And not only that, try to, maybe suppose one algorithm is giving a particular parameter a best, and suppose you are interested in two parameters, and some another algorithm is giving the second parameter as best. Then what point comes to your mind is fusion. Fuse the two algorithms, hybridization of the algorithms, and try to excuse me, try to see how the results are by fusion of this algorithm. And not only that, but maybe try to come up with some new algorithms also, right? So this has been initially, from the initial stage, very, very interesting. So we were discussing calculation of the centroid, calculation of the Euclidean distance, repeat till calculate the new centroid. कब तक करना है ये, till when we need to process, and at what is the point you are supposed to stop, right? So these are the three options wherein what I said, can someone share with me what are the 3 points which you need to consider for stopping the iterations? One.
मैम वो शेप जब तक चेंज ना हो जाए.
Yes, perfect.
Convergence criteria met.
Sorry?
Convergence criteria met.
Conversions criteria met, perfect, absolutely correct. You
Or
set certain parameters in your mind, in your research, and till you converge, right? Till your problem or your algorithm converges, you will go on doing it, right? That's perfect. Anyone else would like to add?
or number of iteration met.
Yes, because see, it is a never-ending process. Suppose you start and you say that I will not stop till my new centroid and old centroid are same. But if the data, if the application is so very different that this is never going to happen, never means maybe very critical, but might not happen. So then it becomes very difficult. So you cannot be so very rigid and say that I will repeat till my new centroid and old centroid are same. No, not possible. Look at the application, look at the data, have the domain knowledge, understand it, and then see Because of course, whenever you're talking about artificial intelligence, machine learning, a lot of human intervention is required. But then when we move ahead towards the deep learning methods, deep learning algorithms, of course, there very less human intervention is required. More focus is on building more accurate and huge data. Now, I will not use the word huge, but I will use the word big data. Bigger the data, better the prediction, better the estimation, better the algorithm, better the results, right? So that is what is very, very important, right? So I'm very happy that whatever I'm trying to discuss with all my researchers, all my participants, it is being very good and nicely taken from your side, perceived, because we are on the same page, right? So moving ahead, I also would like to tell you that whenever we are researching, what I realized is, of course, this is my opinion. What I realized is, it's not always that you have to focus on the algorithm, because there's certain saturation point to it, right? It's not that you have to focus on the algorithm. Of course, you have to focus because it's a very important integral part of your system. But that is not only the thing. Apart from that, there are few other things which are very, very important. But before we proceed, there's one activity for my participants. I request my participants to list down the steps in K-mean clustering. Which are the steps in K-mean clustering? Maybe you can note it down. If you're comfortable, click the picture and share it in the window. I would really like the session to be interactive. Even if you miss one or two steps, it's okay. But it will help me to understand how much we are on the same page, so that the remaining session I can fine tune accordingly. Is it okay with all of you? I'll give you a minute. You will do this activity. Two minutes sufficient to list down the steps in K-mean clustering? Deepak, have you unmuted people?
Yes, ma'am.
Yeah, so I give you 2 minutes to please complete this clustering steps. Hope you're done. Like, can we see some of? Yes, yes, yes. Listing is coming up. Very good. Yes. Choose the centroid, but yes, okay. Select K points. Perfect. Then assume the value of K. Perfect. Very happy. Very happy to see the messages. Yes. I can see a lot of participants are right. See the quality of the cluster.
Hello,
Yes, keep the updating
ma'am.
of the centroid.
Ma'am, how much value the K should we choose initially? 2 or 3 or maybe more than that?
We can choose more than that also. I just gave example 2, 3, 4, but we can choose more than that depending on the application. So moving ahead, am I audible?
Yes, ma'am.
Yeah. So this was the activity, and very happy that all the participants are typing in the message window, and it is very well perceived and taken. Moving ahead, let me list out the algorithm steps for K-mean. You need to select the value of K, randomly assign the K points, compute the Euclidean distance between the k point to the other point, compute the centroid, new k point, repeat again until the error value is within the threshold or no change of the centroids. So whatever we were talking about for previous 10-15 minutes or so, I have listed all this in this particular algorithm steps. Now, when to use k-mean? So k-mean clustering is generally used when you do not have a specific outcome variable that you are trying to predict. You are maybe uncertain, not sure about the specific outcome variable. Instead, say it is used when you have a set of features you want to use to find a collection of observation that share certain similarity or certain similar characteristics. So in this kind of context, in this examples, you use k-mean, right? So again, I'll be little slow. I want each one of my participants to understand that k-mean clustering is used when we are, say, do not have a specific outcome variable that you are trying to predict. Or instead, it is used when we have a set of features you want to use to find the collection of observations. And these observations, whichever are there, they share the similar characteristics. Under this situation, under these circumstances, we will use k-mean. And I said to you that it is not always necessary that you dig in, you work deep into the algorithm and not only in the algorithm. Of course, algorithm end is very, very important, but not only in the algorithm end. There are several other interventions which are required, right? Now, which are those? Feature generation, feature selection, which features to generate, which features to select. Of course, whenever you have the data, you process it, you try to find out the features. Of course, why are we interested in the data? Image में हम क्यों interested है? Speech में क्यों interested है? Why are we interested? Anyone? Or for that matter, in the forecasting, क्यों interested है हम इतना?
Because ma'am, data can give us the insight.
Correct.
A particular
Correct. Absolutely correct. Say, for example, there is an image. In that image, we have apple, oranges, right? I'm interested in that image. Why? Because my application is counting the number of apples, right? So ultimately, मेरे दिमाग में क्या है? मेरा interest किस चीज में है? My interest lies in calculating the number of apples. In that given image frame, 10 apples are there, 12 apples are there. That is what is my outcome from the processing, right? That is my outcome. But why am I interested in that image? क्यों मुझे interest है वो image में? क्योंकि मुझे क्या करना है? एप्पल काउंट करना है. कैसे काउंट करना है? कैसे काउंट करना है? फीचर्स जो है, कौन से फीचर्स है? बहुत सारे फीचर्स रहेंगे उसमें, इमेज में. इन दैट इमेज देयर आर सो मेनी फीचर्स व्हिच आर प्रेजेंट, right? First of all, understanding those features, what I mean to say here is feature generation, feature selection, and I am interested in that image because मेरे features वो image में है. My features lie in that image and I'm interested in that image because I want to extract that features from the image. Because unless I extract those features, say for example shape, apple का shape. If I map the contour or the shape and try to find out अगर circle है orange shape का है, मतलब oval shape है और circle shape है, तो वो oranges है, right? तो I am interested in feature generation and feature selection, right? So now I want you to think of the features. Which features are important? Yes, so I have given you enough time, wherein I had asked that which are the features, how the features are generated, and the feature selection. Now, what is the whole idea? Very interesting. Okay, now I am not only talking about the algorithm, but I am talking about the features. The which are the important features? Of course, there are so many features which are present. Can you see me? Just 1 minute. Can you see the screen?
Yes, ma'am.
Yeah, yeah, let me, yeah. So the features. Now, the idea of feature selection is identifying the subset of the data or transformed data that you want to put into your model. Because see, unless you're right at this stage, which stage? Data set, algorithm level, feature level, identifying the subset of the data or transformed data. If you do this correct at this stage, then rest all will fall in place, right? So here the idea is identifying the features, extracting those features, and so many features are there. You need to be having the domain expertise in a way that out of all these features, which are my most important features for my application in this context, right? Crystal clear. So feature extraction and selection are the most important but underrated steps for machine learning. Once we are right at this stage, better features are better than the algorithm. I'm making a big statement. Better features are better than the better algorithm. See, doing the research at algorithm level, what I observed is we are so much into algorithm, we try to develop so much, and when we are working into artificial intelligence, machine learning, deep learning, it is always our community, like, we always say that data is important, data is important. Of course, it is important. But extracting right features, selecting the important features from the extracted features is very, very important. And I make a big statement here. Better features are better than the better algorithms, because there is a limitation. You're working on the algorithm, hybridizing, novelty, you're adding, you're coming up with your new novel algorithm, fusion, and everything is done nicely. But at feature level, if you have certain lacunas, then your system might not produce a proper result, better result. So here you need to be, I'm giving you a third dimension to understand the research problem. Better features are better than the better algorithms. So getting bigger and bigger data set, of course, is very, very important. But out of whatever is available, the huge data set, big data, the name, rather than huge. Earlier days, we used to use that word, huge data set, but now it is replaced with big data. You might have heard about big data analytics. So big data, bigger data, deep learning, converging into big data analytics and big data processing. So bigger data set, of course, is important, but not only that, there are several aspects to it. Now, what are the other aspects? What are the other examples? User retention. So say, for example, user is using an app for subscription. More the user, of course, see, yeah, you will be able to very nicely correlate to this, what I'm saying. User is using an app and paying for subscription. Now, more the user, more will be the money. Because what is the related parameter? Subscription is proportional to money, means the turnover, right? So target existing customers and new customers, building a prediction model from the existing customers. How many customers are there? How many customers are using the app? Total number of customers. How many have subscribed? How many have paid and subscribed? And the data analytics for understanding the existing customers, bringing in new customers, building a predictive model for the existing customers, and seeing which parameters are lying on and how we are getting the revenue generated out of it, building a prediction model for new customers. Okay, so this is one example which just clicked my mind when I was talking about prediction model for, say, retention, how many customers my app is retaining, right? So building a prediction model for, there are two models which we need to predict, because क्या है हमारे एप्लीकेशन में कितने एग्जिस्टिंग कस्टमर्स है, हाउ मेनी एग्जिस्टिंग कस्टमर्स आर देयर एंड हाउ मेनी न्यू कस्टमर्स आर देयर, ये प्रिडिक्शन मॉडल डेवलप करना है, बिल्ड करना है, एंड we need to find the retention. So here I'm using AIML for building a prediction model, right? Now for user retention, a very nice example I'm giving here. For user retention, feature generation. Some users might have thousands of such actions and other users may have only a few actions. Okay, you will be able to relate this. Those would all be stored in the time-stamped event log. Now, while I am giving the example, this is applicable to many such applications. Whenever you have data logs, time-stamped event logs, you can take that log and analyze. There is one research project with Philips wherein we are analyzing the data log and we are trying to predict if any machine related problem will arise in near future and what kind of problem may arise. So that prediction has been done and that is successfully delivered also. There is one consultancy work from the Philips and wherein the data log, timestamp data log was given and that analysis was done. Not only that, but in our project wherein prediction was to be done, there also time-stamped event logs were there, the data present, which was for 30 minutes, 1 month, 2 months, a year back. All that data log was present and that data log was used for predicting, right? Now need to process this log. We have to do certain pre-processing, data pre-processing. Need to process this log down to a data set with what? With rows and column. If Deepak is there, Deepak will tell at this particular point of time how we got the data from electricity board for different FATA, RA FATA and the other, and how we arrange that data in rows and column. Deepak, are you there? Can you unmute and just speak for a minute? Am I audible?
Yes, you're audible.
Thank you. Thank you. I think Deepak is somewhere into some other thing. So I would like to say that what we did is different regions, data set was available, logs were available. And from that log, we tried to arrange the data set into rows and column into Excel, where each row was some, say, your user, each column was some features. And then what we did is we discussed and then brainstormed and then we analyzed. There are so many features which are available. These are the n number of users and these are the features which are available, right? So moving ahead with feature generation examples. Say, for example, what are the features which we are working on? Number of days the user visited in the first month. Now I'm talking in context with this app. So how do you analyze it? Take the features. Number of days the user visited in the first month. Say amount of time until the second visit. How much time period is, a lag is there, time lag is there, or how frequently the user is revisiting. Number of point on that day, say day J, for say J is equals to 1 to 30. So what is 30? 30 would be 30 separate features, because you need to, it's a complex problem, right? So 30 different features are there. Of course, there are many features, but out of that 30 features, out of that all features, 30 important features we are taking. So total number of points in the first month. some of other features also you are considering, right? And did the user fill out the profile, maybe premium profile, chasing premium profile? If yes or no, because did the user fill means the answer would be either yes or no. So it's in binary, either 1 or 0. And then deep dive into the data like age and gender of the user, whether it's male, female, what's the age group, whether it is 20 plus, 40 plus, 18 plus, like that, and screen size of the device, right? Just a minute.
Ma'am? Hello? Hello?
Yes. Hello, can you hear me?
Yes, ma'am.
Yes. So let us talk about the features, right? And what is the screen size? Now, my dear participants, क्यों चाहिए हमें screen size? Because we want to understand whether the person has joined from mobile, tab, laptop, desktop, right? Again, that is also one parameter on which some things, some predictions are dependent on, right? So this is one example which I gave, right? Now, feature generation or extraction. I said not only data log, but brainstorming is important, because we, being the expert in that domain, we need to understand the data set and list out the features for that particular data set. Total features are listed. Out of those features, say we arrange it in the rows and columns in the Excel sheet, or in some particular format, and then we need to understand which features out of these 1,000 features, which are the most relevant and important, say 25 features, right? Then this leads to the process of feature generation or feature extraction. Once you're extracting the feature, okay, now good to go. Categories are the next thing. Relevant and useful, but it's impossible to capture. So these are the categories wherein you make your feature classify or put your feature into this kind of category. Relevant and useful, possible to log it, and you did. Relevant and useful, possible to log it, but you didn't. Not relevant or useful, but you don't know that and log it. Not relevant or useful, and you either can't capture it or it didn't occur to you, right? So these are different categories. Now for this example, in this context, this could be the categories. So my dear participant friends, I request you to categorize, not now but later on, in the project or in the research work which you are working on. Try to categorize, find out the total features, which are the important features, and categorize those features. Moving ahead, the idea of feature selection is identifying the subset of the data, because see, this is a superset, then this is the subset or transformed data that you want to put into the model. Because see, सारे फीचर्स लेके प्रोसेस करने से कुछ फायदा नहीं है. Why? Because what will happen is, what is important that you are processing, but what is not important that also you are processing, and unnecessarily your model is becoming computationally complex and overloaded, right? Because if you do it in this way, these are the features, but these are my important features. I only model my important features into my model. I put only important features into my model. Good to go now, right? Many redundancies or correlated variables you will observe, right? No need to include the correlated, because see, you have raw data and this pre-processing of the data is very important. Need to construct new variables by transforming the variable. There are two possibilities. One, you may observe redundancies. Many redundancies or correlated variables in your raw data. Quite possible. बार बार रिपीट हो रहा है कुछ इंफॉर्मेशन, रिडंडेंसीज है, Same information is conveyed by 2-3 parameters. Why to take all the parameter? Take the best one, which is giving us optimum and better insight into the values. Choose like that. Redundancies को remove कर दो. Need to construct a new variable by transforming the variable. Sometimes you may see that there are certain things which are revealed directly from the data, but you need to construct new variables by transforming the existing variables. ये भी हम प्री प्रोसेसिंग में करते हैं, डेटा प्री प्रोसेसिंग में. बहुत इंटरेस्टिंग है ये. इसीलिए दैट्स द रीजन डेटा प्री प्रोसेसिंग इज वेरी वेरी difficult and requires domain expertise, because if you have set this stage, if you set this stage correct, the further stages will go correctly. So in this particular electricity project also, we spent a good amount of time in data pre-processing, understanding the data, arranging the data, trying out different models, fitting in this data into different models, analyzing the outputs, right? And at few places, we also constructed new variables and transformed the existing variable, combined the variables, and then we used it in our model, right? So there are certain situations where we also used filters. What is the filter? See, and what are the steps? Filter order possible features with respect to a ranking based on metric or statistic, such as correlation with the outcome variable. Let me make it very simple. क्या करना है हमें? What we need to do is first start with the set of all features. ये सारे मेरे features हैं. Take the set of all features, select the best methods that we did in our electricity forecasting project also, load forecasting. Select the best method. For that, we need to try out different method. Lot of time we utilized in trying out different methods, right? Then we used the machine learning algorithm. Which algorithm is giving us the best performance? Trying to find out. And we tried out with all possible set of features. Feature A, feature B, feature C, feature D, feature E. Started processing it. And then tried, as I said, initially it was learning phase. Initially it was first training phase, then testing phase, then periodic learnings. Because data is growing, our algorithm also becomes smarter. Periodic trainings are also required. So that also we had done. Then there is another feature wherein wrappers are required. Wrapper feature selection, which tries to find subset of the features. So there are two aspects to the wrappers. You may really appreciate when I'm talking about this, because no one will tell you this details, because when you are working on the algorithm, selecting an algorithm to be used for a selected feature is very important. Deciding on the selection criteria or filter to decide that your set feature is good. ये सारा चीज, all these aspects are covered in the wrappers. Two aspects for the wrappers, which you can see: training set. You can see this is the training set. Then these are the feature sets, right? Testing set. You have the feature selection search. You search, certain selection criteria is there. Then you have the feature evaluations, then induction algorithm. And then again, it is like, you have certain hypothesis, you go for feature evaluation, then performance estimation, then again feature set, then you go for feature evaluation, induction, iteratively, right? And that this happens for training set. It also happens for feature set, then induction algorithm. Ultimately, test set is applied, and then final evaluation happens, right? And what is the outcome? You estimate something. What is the accuracy? Or whether you estimate maybe sometimes whether it is correct, or true or false, like that. So this is very, very important, crucial step, wrappers. So what I was talking about is wrappers have two aspects. when I say there needs to be a fusion, only algorithm is not important. Of course, algorithm is important, but only algorithm is not important. And other thing is features and data set. Only features and only data set also will not do good. Fusion of both. Perfect selection of algorithm, perfect selection of the feature, and fusion of both will help. Now, when I say algorithm selection, forward selection, backward estimation, recursive feature elimination, all these methodologies needs to be tried out. Moving ahead, there are certain selection criteria: R square, p value, AIC criteria, BIC criteria, entropy criteria. Whether these criteria are met. Now, I give you 2 minutes to think on what are these criteria and what are the other criteria before we proceed, because we are going to deep dive into all these criteria. Am I audible? Can you hear me? Deepak?
Yes, ma'am. Yes.
Yeah. So I give you 2 minutes to think on these criteria. So, we were talking about, we were talking about the selection criteria. Yes. So there are certain selection criteria, and I had said that these are the standard methodologies or such a certain selection criteria. And maybe you might have used R square, p value, or AIC, BIC, entropy. Entropy, though I'm sure you might have studied this. But moving ahead, uh, there are certain selection criteria and embedded methods Which are those embedded methods? Maybe you are aware that there is decision tree, random forest, but the relation between it, that these are the embedded methods, decision tree and random forest. So a tree-like model, the name itself tells you what is decision tree. It's a tree-like model that illustrates a series of events leading to certain decisions, right? Suppose student, then a tree-like, whether like student, yes or no. If it is a student, if he is a student, yes, then income. No, then what is the income? Income could be high, medium. Income could be low, medium, high. Age less than equal to 30, greater than 30. Credit record, fair, excellent. Age less than or equal to 40, greater than 40. Like that. So this is built in a tree-like fashion. Hence the name is given, right? Because it's a tree, decision tree. Each node represents a test on an attribute, and each branch is an outcome of the test. So here, this is the node. What is the node? Student. What does it represent? It represents a test on one particular attribute. And each branch, this is one branch, this is the another branch, is the outcome of the test. The outcome of the test could be yes, no, high, medium, less than 30. Of course, and then yes or no, age group, yes, no, yes, no. So this is how I can define the decision tree embedded methods. Moving ahead. When we apply this to banking application, who to loan? Not a student. 45 years old, medium income, fair credit record. Who to loan? Student, 27 years old, low income, excellent credit record. So these are different combinations which, on the basis of which the bank decides to provide a loan or not to provide a loan, because there are certain different parameters which are going to drive the decision whether the loan should be given or not given, right, to that particular student or that particular person, right? So I hope you are able to relate to this bank example. Yes or no?
Yes, madam.
Thank you so much. Let's go ahead. Let me show one particular tree. Say, for example, student, no. What about income? Whether the income is high or medium? Medium. Then what will you check? Credit record. If the credit record is, say, fair, or whether it is excellent. Suppose we are routing through this green color path. A credit record is fair, then you will check the age. Whether the age is less than or equal to 40 or whether it is greater than 40. If it is yes, like that, in this particular way. So I just gave you one example. Another example of no. This was yes, right? Of no. Student, that bacha, the applicant is a student, yes, right? If he is not a student, then no question. We gave the loan, right? Not a student. We gave the loan means the bank gave the loan and we have developed this model. Student, yes. Income, low. If it is very low, credit record we are going to check, excellent. But the age group, then again it is low income, excellent credit record, but low income. If that particular is a student, his income itself is low, will not be able to repay the loan amount. So obviously the bank will take the decision as no, loan is not given, right? So this is two criteria I have discussed for the decision tree. And then again, you can also think of some different applications, whether this example I talked about banking application, you can also apply this decision tree for future prediction for, say, whether the day would be hot, sunny, whether wind will be there, what would be the humidity, what would be the temperature, and am I able to play tennis? Suppose I like to play tennis and I want to develop a prediction model, whether I am able to play tennis, say on so and so date. So that is my decision. Yes, no, I'll be able to play tennis or I'll not be able to play tennis, right? It is dependent on so many parameters. Outlook, whether it is sunny, rainy, overcast, or whether it is moderate, that is also there. Temperature, humidity, wind, hot, mild, cool. Humidity, high, normal, low. Wind, weak, strong. Only these two types, right? And depending upon these, whatever existing data set which you have, you will predict. Of course, this is not a very easy prediction. That's the reason, the prediction of our what I would say, the environment department prediction, sometimes whenever it is said that it will heavily rain and it doesn't rain. So of course it is not a very easy task. But yes, of course, if we apply AI/ML algorithms, maybe somehow we'll be able to help and predict it accurately. But still, I will be very transparent in accepting that it is not an easy task to predict the environmental condition. It's a very complex problem, right? So how we will develop the model, or how we will develop the decision tree, and how it will learn, how the learning will happen. So outlook, what are the possibilities? Sunny, overcast, rainy. See, it's very interesting. You parallelly can think in your own mind for the application in which you are researching at present. Immediately try to develop that kind of decision tree. See what is the tree, what are the options, and then again try to build that tree, maybe on the paper or in your mind, whatever applies. So outlook, kaisa hona chahiye outlook? Sunny, overcast, rainy. Then humidity, high, normal, overcast, yes, rainy, wind. Then wind hai to kaisa hai? Strong hai, weak hai? Then ultimate decision would be, yes, I am able to play tennis. No, I am not able to play tennis. Right? So that is the decision tree. So I would, due to short of time, I would like to skip this. And yeah, so we can easily develop the Python decision tree learning algorithms. One is shown here. Very easily, there are certain decision tree learning algorithms which are existing, codes already written. You can use the existing codes, modify those codes, or write your own codes from scratch, whichever is comfortable for you. And try to find out which are the attributes which are better, right? Which are the better attributes and why, and which gives you best results. So entropy of the subset is lower. Then what is the information gain? Then I said about entropy, so you are aware of. Entropy measures the degree of randomness in the data. Because see, whenever the problem is bigger, as I said, it is very, very random. There is a lot of degree of randomness in data. Then what we will use? We'll use the entropy measures. Low entropy, you can see all green apples, low entropy. Here a high entropy, because I can see strawberries, I can see chicos, I can see oranges, I can see green apples, I can see mangoes. So the high entropy, right? Then you know how to calculate entropy. So this is the formula to calculate the entropy. Moving ahead, we can use this entropy for classification. Then information, random forest I was talking about. Quickly, I will touch base upon the random forest ensemble learning with decision tree. Now we have seen the decision tree, and how much time do we have? Last 10 minutes, I would like to wrap up. Ensemble learning with decision tree, right? So there is random forest method, whereas instead of building a single decision tree, what we use is to make predictions, build many slightly different trees and combine their predictions. So we have a single data set. So how do we obtain slightly different trees? Let me show you. Bagging, bootstrapping, aggregating. what we do here, take a random subset of data point from trainings. Is lot of huge work which is happening in this. But due to short of time, I would just like to quickly touch upon and move ahead. Bagging, in that random subset method, fitting the data, bagging the at training time, training, then we apply the DT algorithm, tagging at interface time. This is how we do voting. How much confidence level, whether you are saying how much voting, kitne log bol rahe hai ki with confidence that this is an apple, right? Then training data, random subspace method for training the data, voting, how much is the confidence level, random forest, ensemble learning. That's all from my side. Any questions?
Ma'am, can you talk more about ensemble learning?
Just give me a minute. I have a very nice. Just give me a minute. I will just discuss about it just in 2 minutes. Yes. Yes. So what I was saying is ensemble. There was one good question. Can you see the screen?
Screen is visible, ma'am, but we are on.
Not able to see?
Screen is visible, ma'am.
Sorry. Sorry, I have a bad throat. Let me share. So, are you using this particular method in your application, ma'am?
Yes, ma'am. Actually, I'm trying random forest
Mm-hmm.
earlier for decision making and classification, and
Great.
then ensemble learning is something where I would like to go for different, you can say, high performance parameters,
Mm-hmm.
so that I can optimize the results.
Correct.
XGB, I was just thinking of XGB booster algorithm, and I'm exploring some other methods also which can be applied.
Right.
How to tackle, how to better use them for decision making.
Decision making. Correct. Correct. So you're using decision tree
DT
learning?
I had used on the same data. I applied
Okay.
random forest also, and
Mm-hmm.
there are some friends with whom I am working. So some we had a discussion that we should go for high performance parameters, optimizing the results by tweaking some high performance parameters.
Mm-hmm.
Very much sure about how to use them for optimizing the results. So I heard someone saying that we can use XGP booster,
Correct.
some other methods.
Correct. Correct.
Use them and what is the benefit if we are
Yeah.
using.
Yeah. I would little try to understand which is the data set you're working on and from where you have got the data set.
Actually, the data is for cyber security. We had a raw data also, but we used the data from the Kaggle. And, we try to because for classification we first applied logistic regression type. So because the which algorithm we need to use is not is based on the data we have.
Correct.
How
Absolutely.
that's
Absolutely.
why it was not so we didn't stop there. We applied decision tree. Logistic regression was giving me the better results. Then we tried random forest, but I could see some more research papers where people applied these XGB booster with the ensemble learning.
Ensemble. Yeah. Yeah.
Yeah.
That is a trend. That is a trend wherein
Yes.
people are using.
So I wanted to know more about it so
Yeah.
that
Yeah.
how to use
Definitely.
it and how we can improve the result.
Improve the results. Yeah, perfect, perfect. I understood your problem,
Yeah.
and I understood the context also.
Yeah.
So here, I think you've done the implementation by using Python decision tree learning algorithm. So you've used random forest also, right? So bagging at interfacing it, random subspace method at training time, training the data, calculating, considering two parameters, plotting those two parameters, maybe color, texture, pH value, like this on the basis of these parameters at training set. Then you use the DT learning algorithm, then you understand that yeah, this is how you can classify. Of course then you can say that this section says that these all are oranges, but manually with human intervention, when you see, you can see it is true for all these cases. The cursor is moving, you can see that this is true, that these are all oranges, but for this situation this is not an orange, this is an apple, but it is said to be an orange classified into, so this is a false result. Here also it's a false result, vice versa. In this section, you can see that these are all green apples, wherein we say that these are all apples. But here you can see, of course, this is true, 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 and true, and true, wherein reward, but here false, wherein penalization, right? So this is what is happening in training data when we talk about random subspace method at training time. So random subspace method at basically what is the interface time, whether you are getting a, when you are thresholding or you are trying to analyze which are the locations where you are getting the wrong interface or wrong predictions. So those are obtained, and you can see that at this particular point, Like this, you are getting more insights into the data, and then trying to vote and understand the confidence level. How much percentage of confidence? Like, 66% confidence that this is an apple. Then what is the remaining 100 minus 66? Whatever point, whatever percentage comes, that is saying that it is orange. So it is the percentage at which, and then again, when you train with the data, you are trying to understand and make the algorithm more and more smarter with fine tuning the algorithm and giving the data set properly. So that is how you are going to make it smart whenever you're using the random forest also, right? So this was like background for ensemble learning. Now I'll come to the answer. Ensemble learning method, what we do here is combine multiple learning algorithms. Why we are combining the multiple learning algorithms? See, if you remember in the beginning, I said that suppose I try out for my data set, for my specific application, in this context, I will use one algorithm and I'm getting certain results. I'm happy with it. But what I will do is I will try one more algorithm, right? I will try multiple learning algorithms individually, and then I will see how the results are coming out, right? And then what I will do is I'll combine the multiple learning algorithms. And my dear participants, always this combining the multiple algorithm may lead to better performance or may not lead to the better performance. So here it is detailed analysis which is required. Which parameters are of importance to us in context with the performance? कौन से parameters का performance हमें improve करना है, right? And which multiple learning algorithms will give us best results? कुछ चीजें आपको experiment करके देखनी है multiple learning algorithms में, and at individual algorithms you can analyze it. Detailed in-depth analysis will lead and give you the insights that okay, this algorithm and this particular third algorithm I can combine. So combination of multiple learning algorithm will give better result. Out of the 10, suppose I combine algorithm 1, 3, 5 and 7, I am getting best results, right? So this is what in the ensemble learning you need to try out. Random forests are one of the most common examples of ensemble learning. So when you said you're using random forest, that's the reason I asked, digged into and tried to understand it better. So already you're using random forest, right? So you're doing what kind of learning? Ensemble learning. And it is a very good trend these days, using ensemble learning for complex problems, wherein multiple learning algorithms are combined. But keeping this in mind that performance should improve sometimes, because when I was experimenting, out of 50, 60 permutations and combinations which I tried, almost 30 times it failed in the context with that data. So you need to combine and understand which method works best in your application. So try to have better insight into the data and analyze the algorithm in detail. Do the detailed analysis of individual algorithm to understand that what that algorithm is bringing in your application context, right? So when you're using random forest means, of course, it's nothing but ensemble learning only. So there are certain other commonly used ensemble methods, which is bagging. So I just request you, madam, what you can try is different ensemble methods. Random forest to hai hi, but uske ilawa try bagging, try random subspace method, see how it works, try boostings. What happens in boosting basically? Quickly, I would like to tell you, train the model iteratively while you're making the current model focus on the mistakes. As I said, you reward or you penalize. Means if it is correct, you reward. If it is a mistake, then you again go on changing, right? So train the model iteratively while making the current model focus on the mistakes. It's like how we human being do, na? The way I was yesterday, I'm not like that today, because yesterday sequence, whatever learnings are there, my algorithm human algorithm has updated, isn't it? So the way I was yesterday, I'm not like that today, or how I am today, I will not be tomorrow like that. Every day there is delta improvement, because you learn from your achievements, but the most you learn from the mistakes. Same concept is there in boosting. So what you do is you train the model iteratively while making the current model focus on the mistakes of the previous ones. So पिछले गलतियां जो भी हुई है algorithm में, उस पर से हम सीखते हैं. The algorithm learns from the previous mistakes and increase the weights of the misclassified sample. देखना है कहाँ पे classification अच्छा हो रहा है, कहाँ पे misclassification हो रहा है, और उस हिसाब से we need to fine tune. मतलब you need to increase the weight of the misclassified sample and try to see that जो भी misclassification हो रहा है वो adjust करके fine tune करके whether we are getting the correct result. So madam, I request you to try out these 2-3 methods, common ensemble methods, or maybe in the latest literature you may get different other methods also, but I have come across these 3 very good and powerful ensemble methods. So you may try these methods, fuse it with your particular random forest um, algorithm, try the fusion or combination, and see whether you're getting good results. Thank you so much. I hope I answered your question.
Thank you, madam.
Yeah, thank you. Any other questions? So it's 5:10. Let's wrap up, wind up for today if there are no more questions.
Thank you, ma'am.
Thank you so much. Very wonderful audience you are. Very happy.
Yeah, thank you very much, madam, for giving your time.
Thank you so much. Hope
Thank you very much. Thank you very much, ma'am.
Thank you, sir.
So we'll start the next session after 5 minutes at 5:15.
Sure, sir.
Can I request Deepak or Sanjay sir to just, just make me, I'm a co-host. So if I leave the meeting, it is saying that the meeting will end. So I don't want to disturb everyone. So just, can you please help me? I am co-host. So if I leave, it is
Yeah,
saying
madam, you can leave, madam, no
I can
problem.
leave. Right. Okay.
Yeah,
Thank
yeah.
you. Thank you so
Yeah.
much.
So good evening, everyone. So good evening, everyone. Welcome to the second session of day 2. So in this session, we have Dr. Venkateshwar Rao Kagita sir. So he will discuss about the probabilistic reasoning. So before sir will start, let me introduce Dr. Venkateshwar Rao Kagita. So Dr. Kagita is working as an assistant professor in the Department of CSE, NIT Warangal. He is also one of the young faculty in our department. He has published a good number of papers in very reputed journals like Information Science, and he is also involved in various activities of IEEE. And he has also received a fund of 48.5 lakhs from Department of Science Technology under National Supercomputing Mission project. And he's also having expertise in various fields like machine learning, recommendation system, artificial intelligence. So with this brief introduction, I request Dr. Kagita to start the session.
Yeah, thank you very much, Dr. Sanjay. I hope I am clearly audible and my screen is visible. Am I audible?
Yeah, sir. Please continue.
Yeah. So very good evening, one and all. So in this session, we're going to discuss some of the probabilistic concepts that are important in the context of the machine learning algorithms, as well as the artificial intelligence algorithms and the data science related algorithms. Okay. So we'll start from very basics, and then we will discuss the application of these probability concepts in the machine learning algorithms briefly. All right. So that is the agenda for this particular session. So in this session, we're going to discuss the random variables, both discrete and continuous cases. And we will also discuss the different notions of the probability, like the joint, marginal, and conditional probability distributions, both from the perspective of the discrete random variables as well as the continuous random variables. We'll also discuss properties of the random variables, expectation, variance, covariance, correlation, and some of the example probability distributions also we're going to discuss. So this is the agenda for today's session. So one request to all the participants is that please make the session interactive. If you have any queries, you can unmute yourself at any point of time and ask me any kind of queries. Okay, and if you couldn't follow something also, you can interrupt me and ask me to repeat that. Okay, so feel free to ask any kind of query or interrupt me. So before we start this probability concept, let us try to understand the clear difference between the probability and the statistics, as most of the people have the confusion that what is the difference. All right, so let us start with that. Probability versus the statistics. So probability, all of us are well aware of it. It is the chance of an outcome in an experiment. Experiment could be anything. Experiment could be tossing a coin. Experiment could be throwing a dice. Experiment could be picking a card from the deck of the cards. Experiment could be picking a color ball from the desk of the balls. It could be anything. So in all these examples that I have discussed so far, you are interested in knowing the probability of a random variable taking a certain value. I mean, the probability that the outcome is a certain thing. Like, it means the probability is dealing with predicting the likelihood of the future events. You see that in all the questions that I have posed, like for example, you're tossing a coin. What will be the probability that, what is the probability that the coin will land up on heads? Okay. Or
Sir, your voice is little bit breaking.
Voice is breaking? Voice is not clear, is it?
At our end, voice is clear, sir.
Ma'am, please check your connection. It is clear for others.
Yeah, clear.
Yeah.
Clear, sir, clear.
Okay. Give me a second. So probability is dealing with predicting the likelihood of the future events. What is the probability that the coin will land upon heads? What is the probability that the card pick is a red color card. Okay, all these are you are interested in estimating the likelihood of the future events. Whereas the statistics involves the analysis of the frequency of the past events. Like for example, what are the COVID statistics in the last year, or what are the COVID statistics in a particular region or in a particular time. Okay, or what are the COVID statistics of the whole population based on the sample that you have observed in a particular time in a particular area. Okay, so all these are the analysis of the frequency of the past events. To understand it better, let us go through some of the examples, then it will bring more clarity. So let us first look at the example relevant to the probability. Consider there is a drawer. So let's say that in the drawer, we have got 100 socks. 30 of them are red color, 20 of them are blue color, and 50 of them are black color socks. So it means that there is certain underlying distribution of the socks, and we know that distribution. Okay, so now given this underlying distribution, we are asking questions like, what is the probability that we draw 2 blue socks or 2 red socks from the drawer? Or what is the chance of getting a matching pair if you draw 3 socks? Okay, or what is the probability of drawing 5 socks and all of them are black? Okay, so these are the kind of questions that you ask. So it means that you know what is the underlying model. You're asking questions like what kind of data that you are likely to see based on the model that you have. It means here we know what is the underlying distribution. Based on the underlying distribution, you're asking questions like what are the kind of data that you are likely to see based on the distribution given to us. So these are the kind of questions that you ask in the probability. You know the underlying distribution. So suppose you have no clue about what kind of socks present in the drawer. Then you enter into the realm of statistics. You have no clue about what kind of socks is present in the drawer. Then you enter into the realm of statistics. So the statistics help us to infer the properties of the whole population based on the sample that you have observed. Like for example, so let's say that I have picked a random sample of 10 socks from the drawer. I don't know what kind of socks are present, how many of them are present. I have no clue about any of these things. Okay, so I just picked up 10 socks, and these 10 socks produced 1 blue, 4 red, and 5 black socks. Okay, so from this sample that you have observed, you should be able to infer the properties of the whole population. That means what is the total population of the black, blue, or red socks present in the drawer? It means you're observing a sample. Based on the sample that you're observing, you're trying to infer the properties of the whole population in statistics. Okay, so it means you know the data. It means you have observed the data. You're asking questions like what kind of model would have generated this data? So whereas in case of probability, you know the underlying model, you're asking questions relevant to the data. What kind of data that you're likely to see? Whereas in case of statistics, you know the data, you're observing the data. So once you know the data, you're asking questions like what kind of model would have generated this data? Okay, so that's the basic difference between the probability and the statistics. So in the probability, we are given a model and asked what kind of data we are likely to see. Whereas in case of statistics, we are given a data, not the model, and asked what kind of model is likely to have generated this data. So that's the basic difference. Here is another example to make things more clear. So you have a fair coin, let's say. Fair coin means equal probability of getting heads or the tails. You will toss the coin for 100 times. You're asking questions like what is the probability of getting 60 or more heads, or what is the probability of getting fewer than 40 heads. These are the kind of questions that you ask, and we get a single answer because of the standard computation strategy. Suppose you have a coin of some unknown provenance. It means you don't know whether it is a fair coin or not. The task is to investigate whether it is a fair coin or not. To investigate whether it is a fair coin or not, you toss the coin for 100 times and count the number of heads. So let's say that you count 60 heads. You've got 60 heads. So this 60 heads could be due to the two reasons. One reason is due to the random chance. Another reason, it may be a biased coin. Okay. So which conclusion is correct? So your job as a statistician is to draw conclusions from the data that you have observed. Is it due to the random chance we have got 60 heads? Or is it due to the biasness of the coin we've got the 60 heads? That is what is decided by the statistician. Alright. So in this session, we are more focusing on the probability concepts, okay, and their applications in the artificial intelligence related algorithms. I hope I'm clear so far. Are you guys following? Any queries so far?
Yes, sir. Clear.
Thank you, ma'am. So, what is a random variable? Probability is often associated with at least one event. Event could be tossing a coin, event could be throwing a dice, event could be picking a ball, it could be anything. But the output of this event is random, isn't it? Suppose you toss a coin. Do you know whether it will land upon heads or tails? We are not sure about it, right? Suppose you throw a dice. Do you know whether it will land upon 1 or 2 or 3 or 4 or 5 or 6? We're not sure about it, right? The output is random. Suppose if you use one variable to denote the outcome of this experiment, that is random. Okay, so the outcome of the experiment is random. If you use a variable to denote the outcome of this experiment, we call that variable as a random variable, as it is taking the random values. So a random variable is a variable that assumes the numerical values associated with the random outcomes of an experiment. So you're not sure whether the coin will land upon heads or the tails. It's random. Not sure whether the die will land upon 1 or 2 or 3 or 4 or 5 or 6. It's a random again. So the variable indicating the outcome of this experiment, we call that as a random variable. And this random variable, it can be either a discrete random variable or it can be a continuous random variable based on the kind of data that it is taking. The random variable can be either discrete or it can be continuous. So what is the difference between the discrete random variable and the continuous random variable? Difference between the discrete random variable and the continuous random variable. Discrete random variable takes finite and countable number of values. And if you take any two continuous random variables, it is not possible to get another value which is in between them. Like for example, if you take the outcome of the dice, suppose if I throw a six-faced die, what are the possible outcomes? Possible outcomes could be 1, 2, 3, 4, 5 or 6. Is it possible to get 1.5 or is it possible to get 2.3 or is it possible to get 3.6? It's not possible, right? So the number of outcomes that it takes is the finite and countable number of values. And if you take any two continuous values, it is not possible to get another value which is in between them. So this kind of variables, we call them as a discrete random variables. Okay. Like here are some more examples of the discrete random variables. Suppose if the experiment is making 100 sales calls and let the random variable indicates the number of sales. When you make 100 sales calls, the number of successful calls could be 0, it could be 1, it could be 2, or it could be 3, or it could be 100 as well. But it's not possible to get 1.2 sale, a 3.6 sale, or 4.7 scale like that, isn't it? So this is an example of the discrete case. Similarly, if you inspect 70 radios and let the random variable indicate the number of defective radios, let the random variable indicate the number of defective radios. So if you inspect 70 radios, the number of defective radios could be either 0, or it could be 1, it could be 2, but it can be 1.2 defective, it can be 3.4 defective, something like that. So this is also an example of the discrete case. Similarly, if you answer 33 questions, let the random variable indicate the number of correct. So this is also a kind of discrete random variables. Then comes the continuous random variable. continuous random variable means it can take any value. Like for example, suppose if the random variable indicate the average weight of a class, average weight of a class of 100 people. Okay, so average weight of 100 people could be anything, right? It could be 45, it could be 60, it could be 70, it could be 70.13, it could be 80, it could be 80.99, it could be 90, it could be 90.12345. It can be anything. It can take any value, right? So this comes under the continuous case. Weight, height, price, time, all these are the examples of the continuous random variables. Okay, I hope you got the difference between the discrete random variable and the continuous random variable. Is that clear? Shall we move on?
Yes, sir.
Yeah. We are often interested in knowing the probability of this random variable taking a certain value. Like for example, what is the probability that the card picked is a red color card? Or what is the probability that the coin is taking a value of head or tail? What is the probability that die will land up on 3? What is the probability that average marks are in between 60 to 70? Or what is the probability that average height is greater than 70 kgs? Or what is the probability that height is less than 5 feet? Okay, so we are interested in knowing probability of random variable taking a certain value, probability of a random variable taking a certain value. Okay, so there are different types of probability that we see. The probability can be either marginal probability, or it can be joint probability, or the conditional probability. We try to understand all these probabilities from the point of the discrete case as well as the continuous case. Most of us aware of the discrete cases. We'll also talk about the continuous cases, continuous random variables as well. So what is the marginal probability? Marginal probability is probability of one event irrespective of the other things. Like for example, if I ask a question, what is the probability of picking a red color card? How many total number of cards in the deck of the cards? There are 52 cards, isn't it? Out of them, how many are red color cards? 26 are red color, 26 are black color. So what is the probability of the red? This is equivalent to 1 by 2. So here we are interested in knowing the card color being a red. Okay, so you're not bothering about anything else. It means other aspects of the card. You're not bothering whether it is a diamond or whether it is a heart shape. You're not bothering whether it is a king or queen or 1 or 2 or no, anything else. You're just interested in knowing probability of a particular event. So that is the marginal probability. And what is the joint probability? Joint probability is the intersection of the two or more events. Like for example, if I ask a question, what is the probability of card being a red color king? Okay, king as well as the red color. Okay, can you answer this question? How many total cards? 52. Out of them, how many cards are red and king both? Hello? Can you make this session interactive? How many king?
4 by
Two?
52.
4 or 2?
No, sorry, 2. Yeah, red and I'm sorry, red
Red
and
and king, right? So there is a space of the red color cards, which is basically 1 by 2 or 26 by 52. There is a space of kings, which is 4 by 52, but you are looking for the intersection where both the things happen, which is 2 by 52. Okay, so this is the intersection of the two or more events. So this is the joint probability. Conditional probability is the probability of the one event given that already another event has happened. Suppose if I ask a question, what is the probability of the king given that it is a red color card? It means it is already given to you that it is a red color card. It means you're only looking for the space where there is a match of the red color card. So can you answer this question? Probability of the king given the card is red.
1 by 13.
How many total red color cards?
Sir,
26.
26 total 26 cards are there.
Out of this, 2 are the
2 over the
head.
king.
Yeah,
2 by
1 by
26
13.
equals to 1 by 30.
13, yes, great. Right. I heard it like a 30, that is why I asked. Sorry. Okay, so this is probability of the king given the red color card. Probability of the one event given that another event has already happened. So we'll look at all this again with the help of an example. So here is an experiment of tossing two coins. Sorry, experiment of two events. One is the tossing a coin. Other event is throwing a dice. And this is the joint probability of the die taking a value 1 and coin taking a value heads. Similarly, this is the joint probability of die taking a value 3 and coin taking a value heads. Okay, so given this distribution of these joint probabilities, now suppose if I ask what is the probability of the heads? What is the probability of the heads? It means you're just interested in knowing probability of the heads irrespective of the values that the die is taking. So you're not concerned about whether the die value is 1 or die value is 2 or 3, 4 or 5 or 6. You're only interested in knowing the probability of the heads. Okay, so the marginal probability is the summation over all these joint probabilities where the coin taking a value heads. So this is equivalent to 1 by 2. Similarly, if I ask a question, what is the probability of die equivalent to 6? It means irrespective of the values that the coin is taking, you're only interested in the die value being 6. So you're not concerned whether the coin taking a value heads or coin taking a value tails. So you're only interested in the probability of the die equivalent to 6. You can take the summation over this column wherever the die value is equal to 6. So this is also, we call it as a marginal probability. So this is the probability of heads, which is equivalent to probability of heads comma die equivalent to 1, heads comma die equivalent to 2, and so on, heads comma die equivalent to 6, which is equivalent to 1 by 2. So if I generalize this, if you have the two random variables x and y, if you are interested in knowing a particular marginal probability with respect to a particular variable, this is summation over all the y values and the probability of this joint probabilities. Okay, probability of this joint probabilities. All right. So this we call it as a sum rule. So more formally, we can write it this way: probability of random variable x taking a certain value small x is equivalent to summation over y, probability of x comma y. Okay. Similarly, if you are interested in knowing probability of y taking a certain value y, this is equivalent to summation over x, probability of x equivalent to x comma y equivalent to y. So these two we call them as sum rules. Sum rules. Okay. I hope the marginal probability is clear to everyone. Shall we move on? Is it clear? Any queries so far?
No, sir.
Okay. So next one is the conditional probability, which is the probability of the one event given that another event has already happened. So in the case of the conditional probability, it is important to distinguish between the discrete and the dependent and the independent events, because the intuition is a bit different for both the cases. In the case of conditional probability, it is important to distinguish between dependent and the independent events, because the intuition is a bit different in both the cases. Okay, so let us try to understand the difference between the dependent and the independent events with the help of an example. Let us try to understand the difference between the dependent and the independent events with the help of an example. So let's take an example of the previous. Let's take the previous example, that is two events: throwing a dice and tossing a coin. What is your opinion? Are these two dependent events or the independent events? Tossing a coin and throwing a dice.
Independent.
Independent events? Okay, so why do you think they are the independent events?
As both are different object.
Okay, so it means the outcome of the one experiment is not influencing the outcome of the another experiment.
Right.
Isn't it? That's why we call them as independent events. So like for example, if I ask a question, what is the probability of die equivalent to 6 given the coin equivalent to heads? What is your answer? If the coin value is head, what is the probability of die equal to 6?
1/6.
1 by 6. Suppose if the probability, sorry, die equivalent to 6, but given that the coin equal to 10, this is also 1 by 6.
Right.
What is the probability of die equivalent to 6? This is also 1 by 6. It means the outcome of the coin has no influence on the probability that the die value equal to 6. That is
your
why,
voice is
yeah,
getting
echo, because some of you have, one of you have muted.
echoed.
Because of that, I am getting this echo. Okay. I mean, somebody may be using speaker and they have unmuted themselves. Okay. Now it is clear, right? Is my voice clear? Yeah.
Yes, sir. Yes. Now it is very
So the
clear.
probability of die equivalent to 6, okay, is independent of the values that the coin is taking. That is why we call these two events as the independent events. So this is an example of the independent case. Let us talk another case, that is the dependent events. So let's say that you are picking two cards from a deck. Okay, so let the random variable x the outcome of the first pick. Let the random variable y indicate the outcome of the second pick. And when you are picking the second card, you are not replacing the first card. It means you are picking the second card without replacing the first card. Okay. So now I'm asking a question. What is the probability of the second card being king given that the first card is queen? You're not replacing the first card. Please remember that. It is given to you that the first card picked is a queen, and now you are asking a question that what is the probability of the second card is king given that the first card is queen. You're not replacing the first card. How many total cards? 52. Isn't it? 52 cards. If you have already picked one card, how many cards left? 51.
4/51.
Out of them, 4 are kings. Yeah, 4 by 51 is the answer. Suppose if the given that the first card is king, then what would be the probability?
3/51.
3 by 51. It means the outcome of the one event is influencing the outcome of the another event. So this we call it as the dependent events. If the outcome of the one event is influencing the outcome of another event, we call them as the dependent events. So this is an example for that. Okay. So we use this notation, probability of y given x, okay, to denote this probability that y given x. This notation we use, okay. And there is a interesting relation between the conditional probability and the joint probability. All of you know that. So mathematically, there is a convenient relationship between conditional probability and the joint probability. That is this probability of y given x is equivalent to probability of y comma x divided by probability of x. Okay. Or you can also say probability of x given y is equivalent to probability of x comma y divided by probability of y. Okay. Or more intuitively, you can look at this way. A convenient way to look at this is if you bring this the other side. Okay, this would be probability of x comma y is equivalent to probability of x times probability of y given x. Okay. So this can be interpreted this way. The joint probability is equivalent to probability of the first event times probability of the second event given the first event. Joint probability is equivalent to probability of the first event times the probability of the second event given the first event. Okay. Question to you now. Probability of x comma y and probability of y comma x are the same or they different? X comma Y means X intersection Y. Y comma X means Y intersection X. Are the same or they different?
Sir, it is different.
Different. X comma Y and Y comma X.
Different, sir.
It's the same, right? Intersection. X intersection Y and Y intersection X. Are the same or they different?
Oh, same.
Same only, right? So X comma Y means X intersection Y. Y comma X means Y intersection X. Both of them are same only, right? Either you take X intersection Y or Y intersection X the same. So you can say that probability of X comma Y is equivalent to probability of Y comma X. So using this relationship, okay, intuition, you can write it this way: probability of the first event times the probability of the second event given the first event. Similarly, this can also write it this way: probability of the first event times the probability of the second event given the first event. Both of them are same. So probability of, if you bring this the other side, probability of X given Y is equivalent to probability of Y given X times the probability of X divided by probability of Y. Everybody following, right? So I'm not making it complicated, isn't it? Understanding? Following?
Sir, please repeat.
See, probability of X comma Y is equivalent to probability of Y comma X. Did you get till that point?
Yes, sir.
Yeah, now you're expanding this. X comma Y, probability of X comma Y is probability of the first event. It means the probability of X times the probability of the second event given the first event, probability of Y given X. Similarly, I can also expand this probability of Y times probability of X given Y. Now I'm just taking this value the other side. So I'm writing probability of X comma Y as the probability of Y given X times the probability of X divided by probability of Y. Clear? No, please quickly respond. I will try to explain in different ways. Is it clear or not?
Yes, sir.
Yeah. So this we call it as a Bayesian theorem. Which we use at lots of places in artificial intelligence, machine learning, and data science. Alright. This we call it as a Bayesian theorem. Yeah, the same thing. It may be more intuitive to look at another direction. Joint probability is equivalent to probability of the first event times the probability of the second event given the first event. Okay, so you know that probability of X comma Y is equivalent to probability of Y comma X. So when you expand this, this is how it looks like. So when you bring this probability of Y this side, this would be equivalent to this. This we call it as a Bayesian theorem. I hope how Bayesian theorem is derived is clear to everyone. Is that clear? Shall we move on?
Yes, sir.
Yeah. Okay, so now we will look at the probability distribution. What is probability distribution? Probability distribution is the list of all the possible outcomes of a random variable along with their corresponding probability values. It means it gives an idea of how these probability values are distributed according to the values that the random variable is taking. Like for example, if you take the dice experiment, the possible outcomes are 1, 2, 3, 4, 5, 6. And these are the corresponding probability values of each and every possible value that the die is taking. If you take a fair die, if it is unfair die, there would be a different distribution of these values. That's a different way. So this is an example of the discrete univariate probability distribution with a finite support. Why is it called discrete? This is called discrete because the random variable is taking discrete values. This is called univariate because you are talking about only one experiment, not the multiple experiments or the events. That is why it is univariate. Why is it a finite support? Because it is taking the finite and countable number of values. Okay, so these are some of the axioms that the probability mass function need to be satisfied. So we call this as a probability mass function that gives the distribution of these probability values. there are certain things that the probability mass function need to be satisfied. All of you know about these rules. What should be the range of the probability values? It always in the range of 0 to 1, isn't it? It should be greater than or equal to 0. You should be less than or equal to 1. And if you take the summation over all the probabilities in the distribution, it must be equivalent to 1. It means summation over x, probability of x must be equivalent to 1. Here also you can notice that it is that if you take the summation over all these distributions, this would be equivalent to 1. Okay, so these are the two axioms. Okay, we'll take another example for the discrete probability distribution. Then we will move on to the continuous probability distribution. Here is an experiment of tossing two coins and let the random variable indicate the number of tails. Okay. You toss the two coins, let the random variable indicate the number of tails. So if you toss two coins, what are the possible outcomes? Either both of them are heads, one head, one tail, or one tail, one head, or both of them are tails. Okay. So what are the possible values that the number of tails, if x is a random variable that is counting the number of tails, what are the possible values for it? The number of tails could be 0, the number of tails could be 1, the number of tails could be 2 as well. What is the probability of number of tails equivalent to 0? There are 4 cases. Out of them, in how many cases number of tails equivalent to 0? In only one case, isn't it? Out of these 4 different possibilities, possible alternative cases, in how many cases the number of tails equivalent to 0? Only one case where both the coins are taking a value head. Okay, so 1 by 4 is the probability of that the number of tails equivalent to 0. So similarly, can you tell me what is the probability that the number of tails equivalent to 2? In how many cases the number of tails equivalent to 1? In how many cases the number of tails equivalent to 1? Out of these 4 cases, 2 cases, right? These 2 cases, right? So 2 by 4 is the probability. Similarly, number of tails equivalent to 2, one case, which is this 1 by 4 is the probability. So there are different ways in which you can visualize this probability distributions. Okay, there are different ways in which you can visualize this probability distribution. So one possibility is using the listing. You can have each value and the corresponding probability. Each value and the corresponding probability in terms of a list, as you can see here. You can also express it in terms of the table. Okay, this is one of the familiar thing to us. Number of tails and the corresponding probability distribution. Number of tails and the corresponding probability distribution, and so on. Similarly, the graph, which is the most familiar to us, number of tails 0 and the corresponding probability distribution is 0.25. Number of tails 1, the corresponding probability distribution is 0.5, 2, and the corresponding probability distribution is 0.25. So one more important, most often we don't use it, but it is very much important, especially for the continuous cases. You can also use a formula to visualize the discrete probability distribution or any probability distribution. All right. So if you take this experiment of tossing two coins and a random variable indicating the number of tails. Okay, suppose if I ask a question, what is the probability that the number of tails equivalent to 1? So how many coin tosses? 2 coin tosses. So n equivalent to 2. You're interested in knowing probability of random variable taking value 1. So 2 factorial, according to this formula, I'm substituting n equal to 2, x equivalent to 1. 1 factorial, so 2 minus 1 factorial, which is also 1 factorial. This is the probability of the tail, which is 0.5 to the power x is 1, and 1 minus p, which is also 0.5 to the power 2 minus 1, which is 1. So 2 times 0.5 times 0.5, which is 0.5. Isn't it the same as this? Hello? So do you agree with me that this and this are the same? but different ways of visualization. Hello?
Yes, sir.
Yeah. So this is another way. Using formulas also, you can visualize this discrete probability distributions or any probability distribution. All right. So far we have discussed about the discrete cases, discrete probability distributions. Okay. So here we were interested in knowing the probability of this discrete random variable taking a certain value. Like what is the probability that the number of tails equivalent to 1, or what is the probability that coin will land upon heads, what is the probability that die equivalent to 6. So you are interested in knowing the random variable taking a certain value. Okay, but if you talk about the continuous cases, it is meaningless to ask the probability of a random variable taking a certain value, and most often it is 0 also. So let me give you an example for this case. So let me give my example of the average marks. Let the random variable indicate the number of average marks. Okay. So is it an example of the continuous random variable or the discrete random variable? Average marks. Discrete or continuous?
Continuous.
It is continuous. Let the random variable x indicate the average marks. Suppose if I ask a question, what is the probability that average marks is equivalent to 61.984967? Does it make any sense? And most often it is 0, isn't it? Because the probability that average marks matches exactly to this is 0 most of the times. Hello, am I right? Agree?
Yes, sir.
So for the continuous cases, probability of random variable taking a certain value x is meaningless to ask, and most often it is 0. Okay. So instead, in case of these continuous probabilities, we ask questions like, what is the probability this random variable taking certain range of values? Like for example, I can ask questions like, what is the probability that this average marks are in between 60 to 70? Or what is the probability that the average height is greater than 5 feet? Okay. Or what is the probability that average weight is less than 70 kg? Okay. So you can ask questions like this. Okay. So if you look at this, we call it as a probability density function in case of the continuous probability distribution, which gives the density, how the probability values are distributed. Okay. Like this, as you can see. Most of you may be familiar with this normal distribution, as most of you are either teachers or the students. So both of them are involved in the grading process. So I'm assuming that you know about this, at least normal distribution. That bell-shaped curve you have to get, no? You have to fit the grades into that curve. Okay. So when I ask a question, probability of the random variable taking certain range of values A to B, it means you're interested in knowing the area under the curve which is in between A and B. And the total area under the curve is equivalent to 1. We'll see through the example, then it will be more clear to you. So let's take an example of the metal cylinder production. So there is a company that produces the metal cylinders. There is a company that produces the metal cylinders. And the random variable indicating the diameter of the metal cylinder produced by this company. Diameter of the metal cylinder produced by this company. Random variable is indicating the diameter of the metal cylinder produced by this company. And the diameter of the metal cylinder can be anywhere in between 49.5 to 50.5 centimeters. The diameter of the metal cylinder can be anywhere in between 49.5 to 50.5 centimeters, because it can take any value between 49.5 to 50.5 centimeters. This comes under the continuous case. Okay. And here is a probability density function indicating the distribution of the metal cylinders. Okay. So like the way the probability mass function has to satisfy certain properties, here also probability density function must satisfy certain properties. So probability mass function, there if you remember, p of x must be greater than or equal to 0, less than or equal to 1. Here also f of x must be greater than or equal to 0. And integral over x, f of x dx must be equivalent to 1. Okay, there in the discrete case, summation over x, p of x must be equivalent to 1. Because it's a continuous case, instead of summation, we are taking the integral here. Okay, and here is the probability density function, which is expressing the distribution of this metal cylinder according to their diameter. Okay, so this is the distribution that they follow if the diameter is in between 49.5 to 50.5, and anywhere else it is 0. So this means that there is no metal cylinder with less than 49.5 diameter and greater than 50.5 diameter. All the metal cylinders diameter is in between 49.5 to 50.5. You can visualize the distribution also in the right side figure, as you can see here. According to this distribution, we can see that most of the metal cylinders diameter is around 50. There are very few cylinders with a diameter of 49.5. There are very few cylinders with a diameter of 50.5. And this is how these metal cylinders are distributed according to their diameter. Okay, this is how the metal cylinders are distributed according to the diameter. I hope you understood this probability density function and how it can be visualized with the help of this example. Is that clear? Shall we move on?
No, sir. Sir, this function 1.5 minus 6, it is going to give the negative value?
No, it depends on the x values, madam.
Okay. Okay, I got it.
Yeah. So whether this is a valid probability density function or not. So in order to be valid probability density function, it has to satisfy these properties. It means integral over f of x dx must be equivalent to 1. Okay. So if you take this example, this is f of x. Okay, it means you'll have to do this integral over 1.5 minus 6 times x minus 50 all square dx. And what is the state space? State space is in between 49.5 to 50.5. So 49.5 to 50.5. Okay, so solve this. When you solve this, you will get this. You know, right, how to solve the integrals. If you take the derivative of this, you have to get this. You see that? All right. So now you've got this function. Okay, after solving the integral, let us call it as a capital F of x. Let's say that it is taking the range of values a to b. So how do you solve it? F of b minus f of a, isn't it? So what is b value in this case and what is a value in this case? If this is f of x, what is b value? What is a value?
50.5 B value, A value is 49.5.
50.5 is b value, a value is 49.5. Great. Substitute. This is when you substitute 50.5, you've got 75.5. When you substitute 49.5, we've got 74.5. The difference is 1. Okay, so therefore it is a valid probability density function. Now, if I ask a question, what is the probability that metal cylinder diameter is in between 49.8 to 50.1? How do you solve it? So this is the total area under curve, which is 1. So if you're interested in knowing area under curve, which is in between 49.8 to 50.1, this is the area under the curve you are interested in knowing. So instead of taking this total range of values, you can just take 49.8 and 50.1 and solve for it. This is 0.432, which is highlighted with a blue color region in this figure. My voice is clear now. I have a bit of tongue problem today. That's why I couldn't speak properly, but I hope that is not so bad. You could hear it, right? I mean, clear, right? It is clear, right?
Right.
Yes, sir, clear.
Yeah.
Yes, sir.
Yeah.
Yes, sir. It's perfectly all right.
Thank you. Yeah. So next one is the cumulative distribution function. cumulative distribution function. Okay. Is it okay if I exceed a little more than 7 for you? Based on that, I decide at what speed I have to go. Is it okay if the session is extended little more than what is planned?
Yes, sir.
Yeah. Okay. So cumulative distribution function is the probability of x less than or equal to certain value x. Okay. So we generally use capital F to denote this. F of x is probability of x less than or equal to certain value x. Okay. So if you want to know this, okay, you just have to start from the minus infinity to x and f of it, change the variable to y to avoid the confusion, dx. Okay. Yes, yeah, we changed the variable here. Instead of x, we are taking y to avoid the confusion. 1.5 minus 6 times y minus 50 whole square dy. So if you solve, this is what you got. This is the probability of x less than or equal to x. So it means if I ask a question, f of 50, this means probability of x less than or equal to 50. So you can directly substitute x value is 50 in this equation and you will get this. 1.5 times 50 minus 2 times 50 minus 50, that is 0 whole cube. So this means minus 74.5. This is what? 1.5 times 50, 75 minus 74.5. This is 0.5. Right? So you can imagine that, right? This was 49.5. This is 50.5. This was 50. You're computing this. So this we got 0.5. Okay, using the cumulative distribution function. Understood, right? Understood? If that is understood, I have a question for you. Understood?
Yes, sir.
Suppose I want to know what is the probability of a random variable taking certain range of values, 49.8 to 50.1. Using the cumulative distribution function, f of x. How do you compute? F of 49.8 means what? Probability of x less than or equal to 49.8. What is f of 50.1 means? Probability of x less than or equal to 50.1. But now I am asking, what is the probability that x is in between 49.8 to 50.1? How do you do that? Using these two. F of 49.8, it means this area. If this is 49.8, this is this area. Hello, am I right?
Yes, sir.
Okay, so f of 50.1, if this is 50.1, this is this area.
We subtract it.
Yeah, great. Okay, so this is the total area. 50.1 means you're just interested in knowing this area. Okay, this area. Do you know this area? You know this area. You want to get this area. How do you do it? You subtract 49.8 from 50.1, isn't it? Hello, am I right? So to get this area, see, let's name them. You have got, this is the total area. You know this area, let us call it as A, the total area A. You know this area, which is B. You're interested in knowing C. Okay, you're interested in knowing C. So how do you get C? C is A minus B, isn't it? Hello, agree?
Yes, sir. Yes, sir.
Yeah, so you're subtracting f of 50.1 minus f of 59.8. You will get this area, which is the probability that x taking a value in between 49.8 to 50 point. The same thing here also, 49.7 to 50, f of 50 minus f of 49.7, which is 0.396, which can be graphically visualized like this. The cumulative distribution function is monotonically increasing function like this. This is the probability less than or equal x less than or equal to 50. This is the probability of x less than or equal to 49.7. The difference you take, you will get this range of probability that x taking the range of values 49.7 to 50. Okay. I hope you're following so far. Are you with me so far?
Yes, sir.
Yeah. So the next one is the marginal probability distribution for the continuous case. So if you remember, marginal probability for the discrete case, we have derived the sum rules. If you remember that die and coin example, probability of heads equivalent to probability of heads comma die equivalent to 1 plus probability of heads comma die equivalent to 2 and so forth. So if you generalize this, we have derived the sum rules, probability of x equivalent to summation over probability of x comma y, probability of y equivalent to summation over x, probability of x comma y. So this is easy to visualize for the discrete case. What it means for the marginal, what it means for the continuous case is the question. Okay, so instead of summation over, here we have integral over. But what does it means? Okay, let us try to understand. So here are the two events. X is a random variable of one event, y is the random variable of the another event, random outcome of indicating the random outcome of these two events. Okay, so this is how the instances are distributed according to their x and y values. So if you see the distribution, you can see that most of the instances are at the center, right? At this 0 x value and 0 y value. Okay. So if you see this distribution, the distribution is something like a hill, isn't it? Most of the instances are at the center of the hill. Hello, am I right? Very few instances are around this edges of the hill. Hello?
Yes,
Is
sir.
it right? Yes, right. So now this is the distribution when you talk about the two events. Okay. So, but what is that it means when I say the marginal probability with respect to a particular random variable x? So when I say the probability distribution with respect to x, it means I'm interested in knowing how the instances are distributed according to their x values, irrespective of the values that the y is taking. I repeat this. If I say what is the marginal probability with respect to a particular random variable x, I'm interested in knowing how the instances are distributed according to their x values, irrespective of the values that the y is taking. Okay. So you see that according to the x values also, most of the instances are here. Okay. So as you go this side or that side, the distribution is gradually reducing, as you can notice here. Agree? Most of the instances are here. As we go this side or that side, it is gradually reducing. So this is how the instances are distributed according to their x values. This is how the instances are distributed according to their x values, irrespective of the values that the y is taking. Okay. Similarly, if I talk about the marginal probability with respect to a particular value y, this means that how the instances are distributed according to their y values, means irrespective of the values that the x is taking. You see that most of the instances are at this y value. As we go this side or that side, it is gradually reducing. The distribution or the frequency is gradually reducing. So this is the distribution with respect to y values, as you can notice here. Okay, so that is formally expressed like integral over x probability of x comma y dx. Okay, and the total area under the curve is equivalent to 1. Okay, I mean this total area under the hill, integral over x integral over y probability of x comma y is equivalent to 1. I hope this is clear. What is the marginal probability means in case of the continuous random variables? Is that clear to everybody? Shall we move on? No?
Yes.
Yes, okay, clear. So let's go. Conditional probability. So conditional probability also we have seen with respect to the discrete cases. Discrete cases. Alright. So what it is for the continuous cases. So let us review what is the conditional probability means for the discrete case. So we were talking about the probability of the card being king given that it is a red color card. Okay, and we said it is 2 by 26. Why 26 here? You're only considering the space where there is a match of the red color cards. And as there are only 26 red color cards, the 26 is the denominator here. Okay, so it means what? You're only exploring the space where the given condition matches, right? So if I talk about probability of x given y equivalent to y, it means you're only looking for the row where there is a match of y equivalent to y. Similarly, when you talk about probability of y given x equivalent to x, you're only considering the column where x equivalent to x. Okay, so this is what is the conditional probability in case of the discrete random variable. What it is for the continuous case. What it is for the continuous case. For the continuous case, to understand this, let us take an image example here. Let the distribution is about the distribution of the pixel intensity values at different rows. Okay, so if I talk about probability of x pixel intensity values at a row of y equivalent to y1. So if you see the pixel intensity distribution at y equivalent to y1, you see that there is no intensity here. Okay, but here when it comes here, there is a small intensity values. It's a light red color. Okay, so you see that the distribution here is a very high intensity values, gradually again reducing and zero intensities. Okay, so this is how the intensity values are distributed at this row. Similarly, if you talk about another row, the distribution of the intensity values are different. Okay, you see that the intensity distribution is slightly high here, again going down high, something like this. Okay, as you can see here. Okay, so the probability of the x, okay, changes based on the given underlying distribution. If you take this underlying distribution, the pixel probability of x could be different from this underlying distribution. All right. So is it clear to everybody? So been talking up clear. Shall we move on?
Yes, sir. Yes, sir.
Yeah, we've been talking about the probability concepts from last 1 hour 15 minutes and so. Okay, so where is it used? Okay, so to motivate you, I have a small example here. Taken a classification task. I'm assuming that all of you are familiar with the classification task. Otherwise also I will make it clear. Okay, so we have given the two kinds of insects. One type is katydids, another type is grasshoppers. We have given 5 insects of the 5 katydids and 5 grasshoppers. We have also given a new insect for which we have to find to which class this new insect belong to. So this is a simple example of the binary classification problem. We have to decide to which class this new insect belong to, katydid or the grasshopper. So for any domain of interest, one can extract the features and represent this insect in the numerical format so that the machine can understand easily. Okay, or you can represent it in a feature vector that describes the instance. So for this example, we can extract the features like from the given image of the insect, we can extract the features like what is the color of the insect, what is its abdomen length, what is its throat length, what is its antenna length, whether it has wings or not, what is its mandible size, what is its leg length, what is its pericral diameter. All these are the features that one can extract from the given image of an insect. From the given image of an insect. Okay, so here for the sake of simplicity, I'm taking two features, abdomen length and the antenna length, and representing all these images with the two features, abdomen length and the antenna length. So here are the 10 insects and the corresponding abdomen length, antenna length, and to which class it belongs to. This is the information relevant to the given insects, and this is a new insect for which we only know its abdomen length and the antenna length, but we don't know whether it belongs to the grasshopper class or the katydid class. The task is to identify that or determine that. All right. Is the problem clear to everybody? The binary classification problem that we are discussing here.
Yes.
So now let us see the distribution of these insects according to their abdominal length and the antennal length. So if you see the distribution, this is how the insects are distributed according to their abdominal length and the antennal length. So this is with respect to the 10 insects that we are taking. But if you talk about the more insects, let's say that I have collected the 100 insects, okay, then the distribution would be something like this, okay, as you can visualize in this graph. Again, for the sake of simplicity, I'm only taking one feature, which is the antennal length. I just want to understand how the insects are distributed according to their antennal length. You see that if you look at this antennal length, and as you see the katydids, most of the katydids are at the antennal length of 7. As you go this side or that side, the number of insects are reducing, right? So with this antennal length that I specify here. Similarly, if you see the distribution of the grasshopper according to their antennal length, this is how the grasshoppers are distributed according to their antennal length. So this is the distribution of the katydids according to their antennal length, and this is the distribution of this grasshoppers according to their antennal length. So now can I use the two normal distribution curve to summarize the distribution of the katydids and the grasshoppers? Hello, can I use the two normal distribution curves like this to summarize the distribution of the katydids and the grasshoppers according to their antennal length?
Yes, sir.
Yeah.
Yes, sir.
So this is the underlying distribution which we have got it from the given data. So given this underlying distribution and given a new insect for which we know the antennal length, and the task is to determine whether it belongs to the grasshopper class or whether it belongs to the katydid class. Given this underlying distribution, we have to determine whether the new insect belongs to the grasshopper class or the katydid class. So let us solve it. So here is an example. This is the underlying distribution, and we have given a new insect for which the antennal length is 3. Antennal length is 3. Now we have to decide whether it belongs to the grasshopper class or whether it belongs to the katydid class. Alright. So if this is the antennal length 3, this is the point where the antennal length is 3. What do you think? It should belong to the grasshopper class or the katydid class by observing this distribution, underlying distribution?
Grasshopper.
Grasshopper, because there are more insects with antennal, more grasshoppers with antennal length 3 than the katydids, isn't it? So very few katydids with antennal length 3 and more grasshoppers with antennal length 3 according to this distribution. So the chances are, more chances are there that it belongs to the grasshopper class. But how do you quantify it? You have to quantify it, no? The probability that it belongs to the grasshopper class and probability that it belongs to the katydid class. According to this underlying distribution, there are 2 insects with the type is katydid and 10 insects the type is grasshopper. So the probability that it belongs to the grasshopper class, given that the antennal length is 3, is 10 divided by the total number of insects, 12, which is 0.833. Probability of the katydid given the antennal length 3 is 2 by 12, which is 0.166. Okay, so more chances are that it belongs to the grasshopper class, right? So higher probability that it belongs to the grasshopper class, therefore we assign a label grasshopper. Similarly, if you take another example, here another example with antennal length 7. Okay, so there are 3 insects with 3 grasshoppers with antennal length 7, and 9 katydids with antennal length 9. So the probability of the grasshopper is 3 by 12, and probability of the katydid is 9 by 12, which is 0.75. So which label would you assign, grasshopper or the katydid? Obviously the katydid, right? Higher chance that it belongs to the katydid class. Hello, following, right, everybody?
Yes, sir.
Okay, thank you. So to summarize whatever that we have discussed so far, we have discussed the sum rules in the marginal probability. We have discussed the product rule in the joint probability. We've also derived the Bayesian rule using this sum rule and the product rule. And there is also a chain rule, which is the joint probability of the n events, x1, x2, so on, xn. This is equivalent to probability of the first event times the probability of the second event given the first event times the probability of the third event given the first two events times so on times probability of the nth event given the first n minus 1 events. This is the chain rule, we call it. So any queries so far? Following it?
Yes, sir.
Okay, thank you. Next one that we're going to discuss is the mean or the expected value. Okay, a question to you now. Suppose if I ask you to find out what is the average, how do you compute the average marks of a class if I ask you to do it so? Average marks of a class.
Add all the marks, divide by the number of student.
Add all the marks, total marks divided by the number of students. Okay, alright. That's what we do generally, right? Suppose if I given certain distribution of the marks. Okay, so let's say that there are 100 students. I said that there are 40 students with 50 marks. There are 20 students with 70 marks. There are 10 students with 90 marks. Also, there are 20 students with 40 marks. There are 10 students with 30 marks. I've given you this distribution of the marks. How do you compute the average? Given this distribution, how do you compute the average? I compute the total marks divided by the total number of students. How do you compute the total marks? I said there are 10 students with 30 marks. Okay, it means 10 times 30 I can take plus. There are 20 students with 40 marks. 20 times 40. 40 students with 50 marks. 40 times 50. 20 students with 70 marks. 20 times 70. 10 students with 90 marks. 10 times 90. Will this give the total marks or not? Hello?
Yes, sir.
Yeah. How do you get the total students? 10
100.
plus 20
Huh.
plus 40 plus 20 plus 10 total students, that is 100. Okay. So can I write it this way? Can I write it this way? 30 times 10 by 100 plus 40 times 20 by 100, 50 times 40 by 100. If you have any query, ask directly, no? Don't type in the chat box for now because I can't see the chat box when I am in this screen. What is this? 70 times 20 by 100 plus 90 times 10 by 100. I'm just rewriting this. Can I write it this way? I just expanded it. That's all.
Yes, sir.
So what is this 30, 40, 50, 70, 90? Possible marks, isn't it? Okay, possible values for x. If x is the random variable indicating the marks. What is this 10 by 100, 20 by 100, 40 by 100? Probability of that, isn't it? Probability that probability of the number of probability that marks equivalent to 30, probability that marks equivalent to 40, probability that marks equivalent to 50, isn't it? Okay. So can I say this? If this is x, this is the probability of x. If this is x, this is the probability of x. Okay. So can I write it this way? Summation over x times p of x. Hello? Can I write it this way? Summation over x times p of x?
Yes, sir.
Yeah. So this is the mean or the expected value. This is how we compute. Summation over x times p of x. Alright. To compute the average given a certain underlying distribution. So for the detailed understanding about it, let us go through one more example. It is an example of tossing a single unfair die. Just for the fun, imagine you are tossing an unfair die, and this is the probability distribution of the different faces. Okay, so it means probability of landing on 6 is 0.5. Rest of the faces it is 0.1, 0.1. Okay, so given this underlying distribution, what is the mean or the expected value? It means on an average, what is the value of the die? What value that the die takes on an average? Okay, so summation over x times p of x. What are the possible values for the die example? Possible values for x? 1, 2, 3, 4, 5, 6. What are the corresponding probabilities? 0.1, 0.1, and so on, 0.5. Right. So 1 times 0.1, 0.1, 2 times 0.1, 0.2, next 0.3, 0.4, 0.5. Can you tell me the last one? 6 times
3.
0.5, 3. So this is equivalent to 4 or 4.5. This is the expected value which we denote with E of x. Madam, any query?
No, sir.
No, yeah. So similarly, for the continuous random variables, you can take the integral over x times f of x dx. For the discrete cases, summation over x times p of x. For the continuous cases, integral over x times f of x dx. We'll see that metal cylinder example. Here is the metal cylinder example. This is f of x, x times f of x. If you solve, you will get the average value as 50. That can be visualized also. 49.5, 50.5. On an average, the metal cylinder diameter is 50. That's what it means. Okay. So is the mean value computation is clear both in the continuous and the discrete cases? Mean value computation for a given underlying distribution. Is it clear to everybody?
Yes, sir.
Yeah. So the next one is the variance. So variance measures the spread of the data. So let me give you two data sets and ask a question. This is a data set D1. This is a data set D2. Okay, so which one of these data sets do you think has got more variance?
D1.
Sir.
Yeah, D1 has got more value than D2, right? Why? Because the spread is more in case of data set D1. D1 has got more variance because there is a more spread in the data. So it means the variance is measures the spread of the data. It means how the instances are distributed around the mean. So if this is the mean, we just want to know how the instances are distributed around the mean. Okay. It means mean means what? Expected value, right? E of x. If x is the value, set of values, E of x is the mean value, we want to know how the instances are distributed around the mean. It means we take x minus E of x whole square and the average of this, which is the expected value of this. Okay, suppose if the x values are like this, okay, let's say that the x values are like 2, 1, 3, 4, 5. I want to know the variance. So what is the average? Average is 3 here. Okay, it means the expected value is 3. E of x is 3. Am I right? 2 plus 1, 3, 6, 10, 15 by 5, 3. Yeah, 3. Okay, so we subtract this expected value from each and every value. Okay, so 2 minus 3 minus 1, 1 minus 3 minus 2, 0, 1, 2. Take the square of it, x minus E of x whole square. 1 square 1, 2 square 4, 0, 1, 4. So what is the average of this? Average is 4 plus 4, 8, 10, 10 divided by 5, 2. isn't it? Okay. So understood how to compute the variance? Expected value of x minus e of x whole square. Hello? Understood? Clear?
Sir, understood.
Yes.
Yeah. So now let us simplify this further. So this is what is we have written here. Okay. So this is like a minus b whole square, isn't it? X minus e of x whole square. So can you tell me the formula a minus b whole square? A square plus b
minus 2ab plus b
minus
square.
2ab plus b square. Okay. Using this, can you expand this? X square minus 2 times x times e of x plus e of x whole square. So expand the expectation now. When you expand the expectation, this would be expectation of x square 2 times expectation of x times expectation of x. So expectation of x. So let's say x is this 1, 2, 3. What is the expectation of x? 2, right? Hello. If x is 1, 2, 3, what is the expectation of x? Average of 1, 2, 3.
Yes, sir.
Hello. Not understanding. Lost?
Got, sir.
Expectation of 2 is 2, right? Okay.
Right.
So what is the expectation of x? Expectation of x is 2. What is the expectation of 2? It means what is the average of 2? 2 only, right? Hello? Am I right?
Right. Yes.
This means what? Expectation of x is equivalent to expectation of x. Average of x is average of x. Hello? Am I right?
Yes, sir. Yes.
Yeah. So can I write expectation of x as just expectation of x? And similarly, when you expand this expectation to the other one, which is expectation of x whole square, this is also the same. Expectation of x square. Okay. If you're not understanding, it's okay. Don't worry. I'm just trying to derive in depth. Expectation of x square minus 2 times e of x whole square plus e of x whole square. Minus 2 plus 1. Okay, this is minus 1, right? Expectation of x square minus expectation of x whole square. That's how you got that. Understood, right? Why this is becoming this? E of x square minus e of x whole square. Clear? Hello, everybody. Please respond.
Yes.
Clear. Okay. So we know how to compute expectation of x, which is summation over x times p of x. But how do you compute expectation of x square? Summation over x square times p of x. Okay. This is the variance. Sigma square we use to denote the variance. Standard deviation is the square root of the variance. Square root of this. Okay. Okay. So here is an example to compute the variance. The dice example. Do you remember how much expectation we have got for the dice example? 4.5, right? The sigma square is expectation of x square minus expectation of x whole square. So this is 4.5 whole square. We have to determine this. This is the summation over x square times p of x. What are the possible values for x? 1 to 6. So 1 square times p of x. How much? 1 square times 0.1, 0.1. 2 square times 0.1, 0.4. 3 square times 0.1, 0.9. 4 square times 0.1, 1.6. 5 square times 0.1, 2.5, 6 square times 0.1, 18. Take the summation over this, you will get 23.5 minus 4.5 whole square, which is 18 point something. Okay, so the difference is 18.25, I guess. Okay, so the difference is 3.25. Okay, I think this is 19 point. 3.09. Is it? What is 4.5 whole square? 45, 45. Let me use the calculator. I became weekend. 20.25. 20.25. So this is difference is 3.25. Yes. Okay, this is sigma square. What is sigma? Standard deviation. Square root of 3.25, which is 1.8. Clear the variance of the random variable. Hello. Lost? Hello? Understood or not? There were few participants responding. Now nobody is responding. Is it not clear? Shall we discuss one more time?
Yes, sir, clear.
Clear. Okay.
Clear.
So the next one is the covariance. Covariance is the how one variable is varying with another variable. That's what the covariance measures. Okay. So if I discuss directly formula, you may not understand anything. Let me give you an example. All of you know the e-commerce sites, right? Amazon, Flipkart, where you rate few items in the range of 1 to 5. I just want to understand whether the two users are similar or not. It means whether their ratings are varying with one another or not, whether their ratings are positively varying with one another, whether their ratings are negatively varying with one another. Okay. So when you see this rating patterns, you may be observing different kinds of users, isn't it? Few may be strict users, few may be lenient users, isn't it? Strict users in the sense that it is very hard to satisfy them. If they like the item very much, they give a rating of 3 or 4, not more than that. Okay, most of the times. Similarly, there may be lenient users, kind-hearted people who don't want to give bad ratings, very positive people who don't want to give bad ratings. If they dislike it very much, they give at least 2. Okay, so with this different kinds of users, can I generalize and say that any rating greater than 3 is liked by the corresponding user, any rating less than 3 is disliked by the corresponding user? Can I set a hard threshold like this and say that any rating greater than 3 liked by the user, any rating less than 3 disliked by the user? Can I say that? Hello? No, right?
No.
Because there are different kinds of users. Just now we have discussed, right? But how can I know that whether the user is positive about that item or negative about that item? Can I take the average rating of that user and say compare if any rating greater than his average, he is somewhat positive about that item. Any rating less than his average, he is somewhat negative about this item. Can I say that much?
Yes.
Right. So let us take two users. Yeah. U1 and U2. Let's take very few items just for the sake of simplicity of the example. Let U1 give a rating of 2, 3, 4 to these items respectively. U2 gave a rating of 3, 4, 5. To directly compare the ratings, they are looking like a dissimilar users because they have not given the exact ratings for the different items. Okay, chalo, let us see the rating pattern. Okay, well, their opinion on these items. What is the average rating of user 1? 3. What is the average rating of user 2? 4. 3 plus 4 plus 5 by 2, 3, right? 12 by 3 is 4, okay. Now what is user 1 opinion on item 1? User 1 average rating is 3. User 1 average rating is 3. And he has given a rating of 2 to item 1. Is he positive or negative about this item? He's somewhat negative, right? Because he gave a less than his average rating.
It is negative.
So what about this? 3 minus 3 is 0, neutral opinion. What about this? Is somewhat positive. 4 minus 3. This one. Similarly, you see the user 2 opinion on these items. U2 minus U2 bar. What is user 2 opinion on item 1? Is somewhat negative, right? His average rating is 4, but he has given a rating of 3 to it. 0 plus 1. Okay. Now, whether these two ratings of different users, are they positively varying with one another? Are they negatively varying with one another? It means, have they got a similar opinion? Or have they got a different opinion? So now you multiply the opinions. If both of them get a negative opinion, the result would be positive. Okay. So it means U1 bar, U1 minus U1 bar times U2 minus U2 bar. If both of them are positive, then also it is positive. If one person is positive, the other person is negative, then the resultant would be negative. Okay. So if you get a positive value on an average, it means what? These two users' opinion is matching. They are varying positively with one another. Suppose on an average, if you get a negative value, what is that it means? They are negatively varying with one another. It means they have a difference in opinion. Hello, am I right?
Yes, sir.
Yes, right. So that is what the covariance measures basically. Now let us go back. Let's say that let a random variable x denote the ratings of user 1, random variable y indicate the ratings of user 1, user 2. So average of rating of user 1 means expected value of x. Average ratings of user 2 means expected value of y. So u1 minus u1 bar means x minus e of x. u2 minus u1 bar means y minus e of y. So you're multiplying these two means x minus e of x times y minus e of y. On an average, you are taking this means expected value of x minus e of x times y minus e of y. This is the covariance between x and y. Understood, right? How you got this formula?
Yes, sir.
Right. So now if you expand it and simplify it, you can see the expansion steps later because the time we are running out of time. I'm not going to the details of this, but you just expand this. You might use x times y, x times e of y and expand it. You will get the resultant as e of xy minus e of x times e of y. This is the covariance between x comma y. So please remember, covariance of x comma y is equivalent to expectation of xy minus expectation of x times expectation of y. Okay, so let us solve the problem. So this is the distribution. So the air conditioner servicing company want to understand the relation between servicing time and the number of air conditioning units served. It means increasing the servicing time, is there any improvement in the number of air conditioning units served or not? This is what it want to understand, it want to analyze. Okay. So let the random variable x indicate the servicing time, random variable y indicate the number of air conditioning units served. And these are the joint probability distributions of x and y, and these are the probability values. Okay. This is the probability of x equivalent to 1 and y equivalent to 1, 0.12. Okay. So what is the covariance between x and y? This is basically the expectation of xy minus expectation of x times expectation of y. How do you compute expectation of x? Summation over x times p of x. What are the possible values for x? Possible values for x is 1, 2, 3, 4. So this is equivalent to 1 times probability of x equivalent to 1, 2 times probability of x equivalent to 2, plus 3 times probability of x equivalent to 3, plus 4 times probability of x equivalent to 4. Are you following or overloaded?
Following, sir.
Following, okay. What is probability of x equivalent to 1? Marginal probability of x equivalent to 1, irrespective of the values that the y is taking.
0.12, sir.
0.12 is the joint probability of x equivalent to 1 and y equivalent to 1. I'm just interested in knowing probability of x equivalent to 1, irrespective of the values that the y is taking. What is the marginal probability? How do you compute the marginal probability? Probability of x equivalent to 1 is equivalent to probability of x equivalent to 1 comma y equivalent to 1 plus probability of x equivalent to 1 comma y equivalent to 2 plus probability of x equivalent to 1 comma y equivalent to 3, isn't it? Marginal probability. Do you recall?
Yes, sir.
Yeah, so the summation over this column is the probability of x equivalent to 1, which is 0.21. So 1 times 0.21. Can you tell me x equivalent to 2, probability of x equivalent to 2, 2 times 2, 4.
0.4.
Probability of x equivalent to 3.
0.3.
4 times probability of x equivalent to 4 is
0.25.
0.25. So this is equivalent to 2.59. Okay, similarly, expectation of y, summation over y times the probability of y. What are the possible values for y?
1, 2, and 3.
1, 2, 3. So 1 time probability of y equivalent to 1 plus 2 times the probability of y equivalent to 2 plus 3 times the probability of y equivalent to 3. What is the probability of y equivalent to 1, irrespective of the values that the x is taking?
0.32.
0.32. So, yeah, 0.32. So 1 times 0.32. Y equivalent to 2. 2, 3, 2, 3, 4, 4, 5, 7?
5, 3.
5, 3 or 5, 7?
Wait, sir. Checking.
5, 7 only, no?
5,
Am I
7.
right? 5, 7. 3 times 1, 1.
1, 1.
So this is 1.79. So now the joint expectation. Joint expectation is summation over x, summation over y, probability of x comma y. Possible values for x is 1, 2, 3, 4. Possible values for x, y is 1, 2, 3. So this is 1 time. What is the joint probability of x equal to 1 and y equivalent to 1?
0.1.
0.12. Next, 1 time, 2 time. What is the joint probability of x equal to 1 and y equal to 2?
0.08.
0.08. 1 time, 3 time. Joint probability of x equal to 1 and y equal to 3.
0.01.
So on. Can you tell me the last one?
It is
4 times, 3 times
0.07.
07. So this is 4.86. So you have everything that you require. Substitute 4.86, 2.59, 1.79. This is equivalent to 0.224. Covariance. Clear, right? How to compute the covariance? So the next one is clear or not?
Yes, sir.
Yeah, the next one is the correlation, which is also the similar thing to the covariance, but this is taking a certain range of values, -1 to 1, which is quantifying how much they are varying with one another. Okay, so this is actually normalizing them in the range of -1 to 1. -1 means perfect negative correlation, +1 means perfect positive correlation. If the correlation value close to 1 means high positive correlation. If the correlation value close to -1 means it is a high negative correlation. If the correlation is 0, it means that there is no correlation between them. It means there is no relation between them. They're random. Okay, so you can see the distribution from perfect positive correlation to the perfect negative correlation. So in this, as the x is varying, y is also varying perfectly. Okay. Similarly, here also, as your x is varying, y is also varying the high positive correlation. So the reverse is here. As you increase x, y is decreasing. This is an example of the perfect negative correlation. Okay. So the correlation is similar, but we are normalizing with certain value. That is bringing them in the range of -1 to 1. Okay. So now here is an example. We want to understand the correlation between the temperature and the ice cream cells, ice cream cells. Okay. So how in the cells are increasing or decreasing as you vary the temperature. This is what you want to understand. Just look at the figure and tell me, is there any correlation between the temperature and the cells? If it is so, whether it is a positive correlation or a negative correlation. Temperature and the cells.
Positive.
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 Is it a
Yes.
high positive correlation or a low positive correlation?
High positive.
High positive. It's almost close to, I mean, like the straight line only, right? So here the correlation value is 0.9575. I will tell you how to compute it. Here is the formula. Correlation is covariance of x comma y divided by the square root of variance of x times variance of y. This ranges the values from -1 to 1. -1 means the perfect negative correlation. 1 means the perfect positive correlation. 0 means no correlation. I will simplify the steps for you. So the same example, ice cream example we will taking. So temperature and the corresponding cells. Temperature and the corresponding cells. So very simple to compute the correlation. Give me a second. Okay. First step is compute the means. So let's say this is x, this is y. Okay. Compute the means. It means compute expectation of x, compute expectation of y. Okay. So now subtract the means. So let a is equivalent to x minus e of x. It means 18.7 is the average. You subtracting the average from each and every value. 14.2 minus 18.7 minus 4.5. 16.4 minus 18.7 minus 2.3 and so forth. Okay. Similarly for this column, this is y minus e of y. Okay. So what is covariance? X minus e of x times y minus e of y, isn't it? It means compute a times b, right? Because a is x minus e of x, b is y minus e of y. And the expectation of this that we will do later. What is the variance of x? Variance of x is x minus e of x whole square, isn't it? So it means a square, isn't it? Hello? X minus e of x whole square means a square here, isn't it? Similarly, what is variance of y? Y minus e of y whole square. Hello, following or not?
Yes, sir.
Yes, sir.
So b square, yeah. So take the summation over this, that will be the
Yes, sir.
numerator. Yeah. Take the summation over this. This is the variance of x. Take the summation over this. This is the variance of y. Okay. Can take the average also, but anyhow that will be the same as this, right? So this is 0.9575. This is how you compute the covariance of x comma y, which is a summation over a times b divided by variance of x summation over a square times the summation over b square. Actually it is the average, but because in the numerator and the denominator same denominator will be there, that is why you are taking the summation. Clear, right? How to compute the correlation?
Yes, sir.
Yeah. So here are the sum of the common probability distribution. We're going to discuss some of them. Okay, so give me 20 minutes. It's already 7. So is it okay if I take another 20 minutes, 15 to 20 minutes? I hope that should be fine.
Yes, sir.
Yeah. So some of the discrete probability distributions and what they model: Bernoulli, binomial, multinomial, Poisson, and this is what they model. These are some of the continuous probability distributions. We're going to discuss some of them: uniform and Gaussian distribution. So let us start the distributions directly. Let us start with the most familiar one, binomial. All of us know this binomial distribution, right? It is when you have the fixed number of observations, like for example, you toss 15 tosses of the coin, or observing 20 patients, or 1,000 people are surveyed, like this, when n is fixed. And the outcome is binary every time. Like you toss the coin. Every time you toss the coin, either it is a head or tail, right? Binary, outcome is binary. Similarly, 20 patients are observed. When every patient is observed, you are determining whether the patient has a cancer or not. Binary. 1,000 people are surveyed. Each person said yes or no for a particular question. Okay, that is also binary. Okay, so generally, the two outcomes, we call them as a success and failure. Okay, so P is the probability of the success, 1 minus P is the probability of the failure. And you should have the constant probability for each observation. So suppose you toss the coin 15 times. Every time you toss a coin, probability of heads is same. It's not that one time you toss the coin, the probability of head is 0.5, another time it is 0.6. Then this is not applicable. Every time if the probability is a constant, I mean probability of each observation is constant, probability of head is same in every coin toss. If it is 0.6, it is 0.6 through for all the 15 coin tosses. If it is 0.5, it should be 0.5 for all the 15 coin tosses. Then only this is applicable, otherwise not. Alright. We'll solve the example. Take an example of the 5 coin tosses. What is the probability that you flip exactly 3 heads in 5 coin tosses? Okay, so 5 coin tosses, you should get 3 heads. Can you tell me any such arrangements? Head, 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 tail, tail. This is one possibility, right? First 3 coin tosses are heads, next 2 coin tosses are tails. This is one possibility, right? Can you tell me what is the probability of this possibility? Are these events dependent or independent? 5 coin tosses. Are they dependent or independent?
Independent.
Independent, right? Because the outcome of one coin toss is not influencing the outcome of another coin toss, right? Therefore, they are independent. If the two events A and B independent of one another, what is the joint probability? Probability of A times probability of B, isn't it? So what is the probability of this? Joint probability of this, probability of head times the probability of head times the probability of head times the probability of the tail times the probability of the tail. It means probability of head to the power 3 times the probability of tail to the power 2. Right? So this is the probability of one sequence. Right? How many such arrangements possible? How many ways you can arrange 3 heads in 5 coin tosses? These many number of ways, isn't it? Hello? Am I right? So
Yes.
So, and the probability of each such sequence is this, and this many number of sequences. So the total probability is 5C3 times probability of head to the power 3 times the probability of tail to the power 2. Okay, so let us see here. So this is the probability of, these are the possible ways that you can arrange 3 heads in 5 coin tosses. 10 arrangements are possible, and this is the probability of each such sequence. Probability of head to the power 3, that is 1 by 2 to the power 3 times probability of tail 1 by 2 to the power 2. So this is the 5C3, which is 10. Alright. So 5C3 times probability of heads to the power 3, probability of tails to the power 2. Another question. Voter exit the poll. You ask the representative random sample of 6 voters if they voted for XYZ or not. If the true percentage of voter who who voted for XYZ is 55.1. What is the probability that in your sample, exactly 2 voted for XYZ and 4 did not? How many you asked? 6. Exactly 2 voted for XYZ, 4 did not. How many ways are possible? 62, isn't it? How many ways you can arrange 2s in 6 votes? Hello? How many ways you can arrange 2s in 6 votes? 62 only, right? Array. 2s in 6 votes. This is one possibility. This is another possibility. Like this, 62 ways are there, isn't it? And this is the probability of each and every sequence. So 62 into 0.551 all square times 0.449 all to the power 4. So clear, shall we move on?
Yes, sir.
Please respond. If you are not responding, I will wind up here.
Sir,
Understanding or not?
Yes, sir, understood.
Okay. Okay, fine. So if you generalize this, let's say that there are n trials. Okay, n trials. What is the probability of getting X success? X success out of n trials. Okay, so this is NCX times the probability of success to the power number of success, probability of failure to the power number of failures. Okay, so if you take n trials, what is the probability of getting X success? This is NCX times probability of success to the power number of success, probability of failure to the power number of failures. Okay, so this is what is this. N is the number of trials, X is the number of success, P is the probability of success, 1 minus P is the probability of the failure. X is the number of success, N minus X is the number of failures. So question to you. If I toss a coin for 20 times, what is the probability of getting exactly 10 heads? Assume it is a fair coin. What is N value here? X value here? And probability of X. How many trials? 20. How many success? 10. What is the probability of success? 0.5. So can you tell me probability of getting exactly 10 heads if you toss the coin for 20 times? 20C, 10, 0.5 to the power 10, 0.5 to the power 10. Hello, am I right?
Right, sir.
Yeah. Few more example here, you can go through them later. Bernoulli is the special case of binomial when n equal to 1. So when n equal to 1, if you substitute in this formula, n equal to 1, you substitute in this formula, you get P of X, probability of success as a P. Okay. Probability of failure is X equivalent to 1, which is the probability of success as a P. Probability of failure X equivalent to 0 is 1 minus P. This is a special case of binomial. Multinomial is the generalized version of the binomial. The generalized version of the binomial. So for the binomial, the output should be yes or no, or success or failure. It means binary. The outcome should be binary for the binomial. What if you have more than 2 outcomes? Let's, for example, die outcome. The possible outcomes are 1, 2, 3, 4, 5, 6. More than 2, right? So to model such things, we go for the multinomial. Before we go to the multinomial, so let me try to review this binomial distribution formula. What is that? NCX times, can you tell me? probability of success to the power x, probability of failure to the power number of failures n minus x. If you expand this, this would be equivalent to n factorial by c factorial x factorial times n minus x factorial p to the power x 1 minus p to the power n minus x. Okay, so there are two outcomes. One is the success, the other one is the failure. Okay, and there are total n trials. So n is going here, n factorial. Number of success is x, x is going here. Number of failures is n minus x, which is going here. This is the probability of success to the power number of success, probability of failure to the power number of failures. So this is when two outcomes, success or failure. What if you have more than two outcomes? Let's say that there are three outcomes. There are n trials, there are three outcomes, O1, O2, O3. Okay, so the number of outcome 1 is n1, number of outcome 2 is n2, number of outcome 3 is n3. Like here, number of success is x, number of failure is n minus x. So can you generalize this formula? N factorial by n1 factorial, n2 factorial, n3 factorial. So similar way, number of success, number of failure factorial. Here we have three outcomes. I am taking the factorial of all three. Here probability of success, instead of that I will say probability of output 1 to the power number of output 1, probability of output 2 to the power number of output 2, probability of output 3 to the power n3. So this can be written as 1 minus probability of O1 minus probability of O2, which is probability of O3 to the power n3. Okay. So can you now tell me if there are four outcomes? Can you generalize the formula for four outcomes?
Yes, sir.
N factorial by n1 factorial, n2 factorial,
3 factorial and 4 factorial
n4 factorial
multiplied by corresponding probabilities.
to the power n3, probability of O4 to the power n. Yeah, this is the generalized formula for multinomial. Okay. Let us discuss with an example. It will be more clear. So this is the generalized formula for three variables. We'll solve the example. It will be more clear. If you are randomly choosing 8 people from an audience that contains 50% Democrats, 30% Republicans, 20% Green Party members, what is the probability of choosing exactly 4 Democrats, 3 Republicans, and 1 Green Party member? Can you tell me what is N, what is N1, N2, N3, and what is the probability of output 1, probability of output 2, output 3? What is N?
8,
8. What is N1?
4,
N2?
3,
N3?
1.
What is the probability of Democrats?
0.5,
0.5. Republicans? 0.3.
0.3.
Green Party members? 0.2. Okay. So probability that Democrats 4, Republicans 3, Green Party member 1 is n factorial divided by number of Democrats 4 factorial, number of Republicans 3 factorial, number of Green Party members 1 factorial. This is the probability of Democrats to the power number of Democrats, probability of Republicans to the power number of Republicans, probability of Green Party members to the power number of Green Party members. Okay, clear, right? Multinomial. Hello, everybody. Clear?
Yes, sir.
So please pay attention for another 5 to 10 minutes. I will wind up. Okay, I don't want to leave it half complete. Let us bring some logical conclusion to this. 5 to 10 minutes, please bear with me.
Yes, sir.
Poisson distribution is for the counts. Okay, number of events per unit. Like for example, number of customers arriving in 20 minutes, number of strikes per year in India, number of defects for 1000 DVDs, something like that. Okay, We'll solve example, it will be clear. This is the distribution. Probability of x is lambda to the power x times e to the power minus lambda divided by x factorial. Lambda is the mean number of events in the unit. E is base of the natural logarithm, which is 2.71. X is the number of events per unit. You may not understand this way. We'll solve the example. Customers arrive at the rate of 72 per hour. What is the probability of 4 customers arriving in 3 minutes? Here the unit is 3 minutes. Okay. 72 per hour. What is the probability of 4 customers arriving in 3 minutes? 72 per hour. It means 60 minutes. How many for 1 minute? 1.2. 72 by 60, 1.2. Right. How many for 3 minutes? 3 times 1.2, 3.6. Okay, so here the unit is 3 minutes. So the mean number of events per unit, which is lambda, is equivalent to 3.6. Number of events per unit. We are interested in knowing 4 customers arriving in 3 minutes. So x equal to 4. Lambda is 3.6, x equivalent to 4. Substitute. Okay, so this is 0.1912. Clear, right? Hello. Should I repeat? Or clear?
Yes, sir.
Uniform probability distribution. This is there in both discrete as well as the continuous. We're going to discuss it in the continuous case. So let's say that you are traveling from Chicago to New York. The flight can arrive anywhere in between 120 to 140 minutes. Okay, the flight arrival is in between any time between, under normal conditions, the flight time is in between 120 to 140 minutes. Because the flight can arrive anywhere in between 120 to 140 minutes, this comes under the continuous case. Okay, with every minute being equally likely. Okay, so what is the probability of the flight arriving in that minute? 120 to 140. How many minutes are there? 20. What is the probability of flight arriving in a particular minute? 1 by 20. If x is in between 120 to 140 minutes. Isn't it? Anywhere else it is 0. So this is the distribution, with every 1 minute being equally likely. Flight arriving in that particular minute is 1 by 20, 0 anywhere else. Right? 0 anywhere else. Alright. So if you generalize this, probability of x is in between a to b is 1 by b minus a, 0 anywhere else. So what is b for our example? 140. A for our example is 120. So 1 by b minus a, 1 by 140 minus 120, which is 1 by 20. That is how you got this 1 by 20. Okay. So this is the distribution, uniformly distributed. A question to you now. What is the probability that flight will arrive in between 125 to 135 minutes? Which means you are interested in knowing the area under the curve, which is in between 125 to 135 minutes. Can anybody answer this question?
Is it 1 by 10?
1 by 10. So let's see that 1 by 2, right? What, this is looking like a rectangle or not? Isn't it looking like a rectangle? You want to know the area of the rectangle. How do you do it? Length into width. What is the length here? 1 by 20. What is the width here?
10.
10. 135 to minus 125, which is 10. So 10 times 1 by 20, which is 1 by 2. What is the probability that flight will arrive in between 130 to 135 minutes?
1 by 4?
1 by 4. So 5 times 1 by 20, which is 1 by. The same thing. Here is completed. Normal, the last one. Hold on for 5 minutes. I will wind up the session. Normal distribution, most of us know, it is most widely used. okay, to model the variables as well as the some statistical inferences. Okay, so it is widely used in varieties of application because most of the things in our life, day-to-day life, follows this normal distribution. Like for example, height of a people, weight of a people, time taken, all this follows the normal distribution. Most of the people are at average weight. Most of the people are at average height. Very few people are tall. Very few people are short. Something like. Okay, so height of a people, amount of rainfalls, test scores, scientific measurements. All this follows the normal distribution. We use this. This is the formula, probability density function for the normal distribution. Mu is the mean. Sigma is the standard deviation. E is the base of the natural logarithm, 2.71. Pi is the pi value, 3.14. Characteristics are it is a bell-shaped curve, symmetric, something like this. Okay, so the family of the normal distribution are defined by the mean value and the standard deviation. Mean is the central value, standard deviation determines the spread of the data. Highest point is at the middle of the curve, which is also the mean, median, mode. This is the highest point. The mean can be any numerical value. It could be either negative, it could be 0, it could be positive. So here is the negative value mean, a curve with the negative mean. This is the curve with the 0 mean. This is the curve with the positive mean. Okay, so higher the width of the curve determines the standard deviation. Wider and flatter curve means more standard deviation. Thinner and taller means the less standard deviation. So the probability of the normal random variable is given by the area under the curve, which is a symmetric, exactly 0.5 to the left of the mean, 0.5 to the right of the mean. Standard normal distribution is the special case with a mean mu equal to 0, standard deviation is equal to 1. We generally use letter Z to denote the standard normal distribution. Letter Z. This is the cumulative probability. Probability of Z less than or equal to 1 means the area under the curve left to the 1. Area under the curve left to the 1, which is highlighted with this blue shaded region in the figure. Left to the 1. For the standard normal random variables, generally the cumulative distribution table is known to us. So this is the table. It looks something like this. I will tell you how to refer to the table. Probability of Z less than or equal to 1.1, let's say. So look at the Z value, 1.1. This is the second decimal point, 0.0. This is how you refer. So can you now tell me what is the probability of Z less than or equal to 1.12? Refer to the table and tell me 1.12, 0.8686. Now you please answer this question. What is the probability of Z less than or equal to 1.22? Anybody? 22. 1.22. Z less than or equal to 1.22.
Will it be 0.8888?
8888. Okay. Thanks. So please take the photograph of this. We'll solve two problems and wind it up. This is the distribution table. You take the photograph of this quickly and let me know.
Taken, sir.
Taken? Okay. What is the probability of Z less than or equal to 2.46? Direct from the table. 2.46. Two point four six 9931 0.9931. Okay. What is the probability of Z greater than or equal to 2.46? It means less than or equal to 2.46 means the area under the curve left to this. Greater than 2.46 means this area. What is the total area under the curve?
1.
1. You know what is the left to the curve, which is 0.9931. No? What was that? 9931, yeah. So what is the area under the curve right to this? 1 minus 0.9931, isn't it? Which is 0.0069. Clear, right? So what is the probability of z less than or equal to minus 1.29? You can't get it directly from the table. So you remember, this is I said one of the properties, it is a symmetric. So area under curve less than minus 1.29 is same as area under the curve greater than 1.29. I mean, this red shaded region is same as the green shaded region, right? Hello, am I right?
Yes, sir. Yes, sir.
So how do you get the area of this green shaded region? The total area under the curve is 1. Okay. So if you ignore this green shaded region and rest of the thing, what is that? Probability of z less than or equal to 1.29, which is this area. This area, isn't it? This total area. So what is that? Z less than or equal to 1.29? Is it 9015? What is that? 1.2. 9015, right? So 1 minus 0.9015, which is 0.985. Similarly, if I ask a question, what is the probability of z greater than or equal to minus 1.29, which means this area. Okay. So probability of z greater than or equal to minus 1.29 is same as probability of z less than or equal to 1.29. So z less than or equal to 1.29 is 0.9015. Okay, so like this you can solve the questions. These are the references. So thank you very much and happy learning. If you have any queries, I can take up. Otherwise, we can wind up the session. Thanks for the opportunity, sir. And I hope you guys followed the session and enjoyed it. If you